A very warm welcome. Okay. A very warm welcome and a very good morning to all the participants of BAR 2020. It is the last and final day of the workshop. Today in this session, we have with us a great researcher and a reputed industry expert, Dr. Praful Pai. A brief bio about Dr. Praful Pai. He is associated with academic engineering team at MathWorks India, where he primarily works with academia in India towards making STEM education engaging and accelerating research with MATLAB and Simulink. He completed his undergraduate studies in biomedical engineering from Manipal Institute of Technology and his MS and PhD from Department of Electronics and Electrical Communication Engineering at Indian Institute of Technology, Kharagpur, focusing on non-invasive blood glucose monitoring with photoacoustics. Prior to joining MathWorks, he was an R&D engineer, later a research scientist at National Brain Research Center, Gurgaon, where he worked on developing an MRI brain template from Indian population. He's passionate about learning, teaching, and research in multidisciplinary domains involving instrumentation, signal and image processing, statistics and optimization, and machine learning. Sir, I welcome you to this workshop BAR 2020, and I would request you to kindly proceed towards the talk.
Uh, Thank you, Professor Maz and Professor Day, for giving me the opportunity to talk at BAR 2020 at NIT Silchar. So it's indeed a great pleasure to kind of present here and also talk to interact with the audience who is watching on the live stream. So let me just start sharing. So
yes, sir, it is visible.
Sure. Let me just switch off the camera as well, just to preserve bandwidth. Yeah. So thank you for that very generous introduction, Professor Mal. So today, as Professor Mal mentioned, my name is Praful, and I work with the academic engineering team at MathWorks. What we do is mainly work with faculty members, students, researchers such as yourselves who are joining in the call for accelerating their research across several different domains. Today we are going to be talking mostly on modeling and simulation for medical devices and diagnostics. So before we begin, so I just mentioned that you can use the comments on the YouTube live stream for your Q&A, and we'll possibly address this at the end. And I do think we'll have some time remaining, so we can do that. You'll receive any presentation and code, so I'll share these with Professor Day, and so you don't have to worry about that. And any information on using MATLAB or accessing MATLAB and Simulink, or placing requests for trials, I'll briefly highlight this at the end. But today I want to focus more on the modeling and simulation bit, and so on. Yeah. And in any case, if there are any questions which I leave unanswered, or in case something crops up later on, you can always please feel free to email me at this email. I'll highlight this again at the very end. Uh, this is the brief agenda that I thought of covering today. Mainly, look at the challenges with medical device development, and look at model-based design with MATLAB and Simulink. Uh, and I'll introduce you to modeling and simulation during this time as well. And we'll look at some examples in action, mainly looking at a ventilator example as well as an emergency bed. We'll highlight briefly code generation and deployment, and share with you a few resources to get started with this. So, uh, being from Kharagpur, like I saw, a whole gamut of speakers who are very familiar. I think so. Like In case you were looking at expecting something on deep learning or machine learning, so I recently gave a talk at NIT Silchar at one of the other workshops. So the links are embedded for the presentation here, so you can there's one talk on deep learning and another one on machine learning, so you can view this via the link. So moving on to medical device development. So why is medical device development hard, and why does it take too long? So if we look at any sort of modern medical devices or diagnostics that we have with us, you'll notice that they have very long development cycles, and also companies go have to jump through a lot of hoops to kind of to get from a research stage to a stage where it is commercialized and available for an end user like a hospital or a clinic to purchase, right? So why does it take this long? That primarily boils down to the safety critical nature of these products. So if you look at product classification in terms of classes, there are class 1, 2, or 3 devices as defined by the US Food and Drug Administration. And if some countries like China and so on also have a class 4, or they differentiate between uh, uh, four separate classes, depending upon the critical nature or the risk to the user. Right? Very often, or I would say almost always, this medical device or has a very complex design, and it would involve multiple domains coming together for the end product, right? So it takes a very complex or a very multidisciplinary team to go from to start from system requirements to prototype to final product, right? There are multiple regulatory hoops which you might have to follow through in terms of some FDA requirements, some IEC requirements or electrotechnical commission standards which you have to adhere to, or ISO standards that you have to adhere to, and to do this with a development team, a large development team in an industrial setting, maybe so wherein there are multiple teams working with each other and sharing code, doing their own bit, and so on. Right? So while all of these are very relevant to an industry, uh, I wanted to talk to you about how some aspects of these might be relevant to you in an academic setting as well. So we as researchers, engineers, and scientists, uh, uh, we work on a specific aspect of a particular medical device, or say an algorithm, and we also would like to uh, see our research or our work commercialized or reach the end user, right? So uh, I, my main objective of highlighting these steps was to uh, like let you know of these multiple steps which might be involved, and maybe when doing your research or trying to develop that algorithm itself, uh, look at steps that you can take with minimal overhead, which can help accelerate it, is which can help accelerate your research itself, and also make it more acceptable to an industrial partner who is coming in and who is looking to help you commercialize that. Right? So um, so like uh, essentially you would want to not just uh, do the algorithm development fast, but also hand it over to a commercial partner. So get to the prototype stage really fast and hand over the prototype to a commercial partner, so that they can take forward the development. Right. So mm, and with the larger role that industry and academia are trying to play together in terms of joint projects, consultancy projects, and so on. So I think this makes it really relevant. Uh, but it's also, during the course of this talk, you'll also see that how it is relevant just for the sake of research itself as well, right? So during in addition to all of these like challenges that medical device development faces, so there are also multiple recalls. So if we just look at the FDA data for medical devices which are recalled, so again, devices are broadly classified into three classes: class 1, 2, and 3, depending upon the increasing nature of severity or risk to the particular uh, user. All right. And as you can see, over time, the number of class 3 devices has remained more or less constant, like less than 100. But the number of class 1 and class 2 devices has continued to increase. Uh, class 2 devices mainly. Uh, However, we also see that the number of recalls for these devices have also doubled, like also increased. Okay. So class 1 and class 2 devices are low or moderate risk to the end user. So why are these devices even being recalled? That is primarily, if you look at the reasons for recall, that is primarily due to changes or faults in design, or changes in the control system or process control that are implemented in terms of packaging issues. But primarily, the recalls are due to changes of a very critical nature in the functioning of the device itself. Right. So, how is that related to us as engineers or researchers, scientists? So, if you think of designing systems itself, right? So we very often like to describe our system with a bunch of code, right? So maybe we may be developing a signal processing algorithm for denoising images, or we may be developing an image processing algorithm for finding out whether there is a tumor in a particular region of the body, or it might be any sort of we might be trying to model a mechanical system or a control system, right? And we very often do that with a bunch of code, right? Uh, Often our code is not just one single program. It's not just one single file. It is multiple files, right? It is a bunch of function files, a bunch of data files, a bunch of specifications that it has to read, and so on, right? And often this code for one particular part of the system has to interact with codes for other parts. Like, so in case you were writing something for, say, tumor detection, then in image, so you might have a bunch of code for reading an image. Uh, you might have a bunch of code for doing some pre-processing, uh, something for doing analysis and isolating the region with the tumor, and finally something to interface that your results and put it out to the external world in a manner such that the end user understands it. So, like say a PACT system or a any sort of hospital administration system, right? So, uh, so very often your system involves multiple subsystems, and each of which has its own sort of algorithms, has its own sort of backend design, which exchange data with each other, right? And a smaller subsystem might be required to fit into a larger device, right? So there might be a bunch of data coming in, and you may have to kind of go through multiple uh, before it makes any sort of meaningful sense. It might have to go through multiple subsystems which interact with each other, right? So even though we as researchers think of our algorithms as very uh, small or very or by themselves as having existing independent of everything else, if we just think about it for a little bit more time, or think about partitioning our algorithm development into different stages, we'll often see that we do have at least 3 to 4 steps in even a simple signal processing algorithm, right? So why are we even talking about this? So that is because it is inherently linked to the challenge of medical device development or any device development, wherein we move from requirements, gathering requirements for a particular device, uh, going on to our specifications, then doing the actual work for designing the system, and coding it, maybe coding over different platforms, and then realizing it onto hardware or software or a cloud-based apparatus and so on, right? So, apologies for that. So we'll see that most of the errors are introduced early in the design phase, right? And unit testing or some amount of common sense testing has helps us find some errors, but most of them are found late when we are bringing multiple parts of the system together for integration, right? And these late errors cost more, right? So um, if you just see this graph of like the relative cost to fix an error in software, or wherein the error might be related to say some sort of requirements or some sort of design changes or coding changes, you'll see that very often, if you find it early in the design process, your cost is lesser. While if you kind of stay on, if you let the errors propagate through your entire development process, and if you try to address them at the very end, the errors increase a lot. Why is it relevant to us as biomedical researchers? That is relevant because, so say very often research is a very non-linear process, right? So we might start with a particular looking at a particular algorithm or looking at a particular sort of objective, but very often that particular objective changes during the develop as you kind of progress through your research journey, right? So very often the requirements themselves might change. Um, you might need to change some sort of programs in between or at the very end, say if you're developing an algorithm for CT images, but at the end very end you may have to kind of uh, switch over to using the same algorithm for MRI images instead, because you didn't find a CT image database big enough for this. So uh, so then there might be changes which might be required for you to do in your entire process for it to work better, right? So So even as researchers, even though we do not uh, do all three of these in terms of how an industry does, but inherently in our mind we do uh, we do divide our task into somewhat of these three stages. Like we do define our requirements. We think of what our project or what our algorithm will do. We do think of how we might design it, how we might code it, how we might implement it, and then we do the actual coding and implementation bit. Right. So, in terms of medical device development, let's look at how a traditional design process works. So right now, in the research domain itself, there are multiple research labs at different academic institutes which have a very multidisciplinary group. Right, there are students from the electrical engineering or electronics engineering combined with students from mechanical engineering who are working jointly, maybe on a project. Right, there might be control system engineers. There might be something like engineers who work just on data analytics or image processing or signal processing, right? So in the traditional design process, say if these bunch of engineers are trying to achieve a particular task or like realize a particular project, so you start from your requirements phase, gather what is it that you want to achieve, and move on to your design. Like, you design some control aspects, some mechanical aspects. There might be electrical aspects involved. There might be some data analytics which is involved in there. If there are any control algorithms or any sort of uh, you know uh, any sort of algorithms which are say some signal processing algorithm which is involved, you may ultimately need to implement it on some end hardware, right? So maybe an embedded system of some sort, or maybe FPGA, or maybe a GPU, because you need that fast processing to be there, right? Um, and finally, once you have implemented your algorithms or thing in code, you look at integration and testing of the device. So you look at how you can bring everything, all of these things together: your control algorithms, your mechanical and electrical components, everything together, and see if your system, or see if your end process is realized or it functions as what you thought it would, right? So very often there are multiple barriers in this process, right? We might start with a set of requirements, but when designing the system, we do not really think of validating it against the requirements that we started off. So this definitely happens with all of us. At least it happens to me, I'd say. Like, I get, so we as engineers or we as scientists, we get we get excited about developing new algorithms. So it is very hard, and then the algorithm development process itself takes on its own sort of dimension. So we very often we don't go back, and we may not check what we were trying to achieve. So designs might be very hard to validate against your system requirements, right? If you're looking at coding things, and say you may need to code it for different platforms. Say you were trying to realize a signal processing algorithm, and you thought initially that maybe an embedded platform, say a DSP or a microprocessor might be enough for processing your inputs. However, very soon you realize that you might need to opt for a faster platform. You may want a GPU to do that, or maybe an FPGA to do that, because the latency that is required is very low. Um, so in that case, you may switching from one coding for one platform to coding for other platforms might be really slow. Right? And there might you are definitely not expected to be experts in multiple coding for multiple platforms. Right? Very often we do just one thing and we try to do it well. Right? So manual coding is slow, and again, every time we go for manual coding, it's introduces defects, and it's difficult to compare it to your design. Right? And mainly we as like many of us might not really be comfortable talking to people from different domains, right? So like say if we are designing a project on our own, so the control systems engineers need to be able to talk to the mechanical and the electrical engineering folks, the data analytics folks, so that uh, everyone is on the same page and everyone is working towards a common goal, instead of developing their own subsystems by themselves and then realizing that they might not talk to each other that well, that the subsystems might not function in a cohesive manner with each other, right? So you cannot really kind of optimize your system performance or detect any sort of integration issues if everyone works in silos, right? And you may find errors very late in the development process, and you may need multiple prototypes to do that, right? So you can't in the research world itself, you can't really uh, like you look at developing multiple prototypes and see if they function uh, well, or they function as per requirements, right? So we don't really have the time, as well as we don't really have the financial resources to build multiple prototypes. So we need to be able to build fewer prototypes, and the prototypes that we do design and we do build, they need to be as close to what we want to finally uh, achieve, right? So to get to address these problems, there is a process known as the model based design process. um, So I'll just highlight what components go into the model-based design process. And this process involves modeling and simulation heavily. Uh, we'll just see what it does. Right? So basically, if uh, it it envisages a common single platform for different teams to do their system level design. So instead of thinking of only your particular algorithm or your particular code, you also think at a system at the level of a system, and how will it fit with uh, other like parts of the project, right? And you do simulations to optimize your system performance, all right? If you look at implementation, then you look at saving time by automatically generating code for different platforms. Might be embedded platforms, might be FPGAs or programmable logic controllers, and so on. Right? And you also can lower costs by, instead of prototyping over and over, you can use a hardware in loop testing. So basically, you model your real world in hardware, like how a real world system might behave, how there might be noise in a real world system, or uh, basically replace the environment that your device or algorithm is going to be placed in, and replace that environment with a HIL system, and then see how your algorithm or your device performs in that setting, and use that for iterating on your project. Right? And finally, test everything at each level against the requirements. Right? You know, so this will lead to a better design process, and it will help you to compare your designs to your specifications. So in the academic setting, we might not really do all of these tasks, but we very often we do require some amount of uh, like some amount of each of these things, right? We some amount of system level design, some implementation, some integration, and some verification against requirements. Right? So this is where MATLAB and Simulink come in. So I'm sure most of you are MATLAB users already. So just to give you an overview of what MATLAB and Simulink can do. So MATLAB is the base product, which is built on C, C++, and mainly helps you do mathematical computation, statistical analysis, data visualization, and so on and so forth. Like, built on top of MATLAB is Simulink, which is basically a simulation and modeling environment. It is more, it's a graphical way of programming things, I'd say, but that's simply not it. Uh, we'll see more. You'll see what I mean when we get to that. So basically, it's a simulation and model-based environment which brings together multiple different modeling domains. You can make event-based models or physical models in Simulink. And both MATLAB and Simulink enable parallel computing as well as code generation. Like you can generate code for different platforms using both of these, or you can also scale up your programs or your MATLAB programs or your Simulink models to multiple CPUs or GPUs and so on, or even to the cloud. Okay. So, and these enable applications across different domains. Okay. So we'll focus mostly on Simulink in during our talk today. So as I said, it's a graphical programming environment and allows you to design and simulate your system before moving into production. Okay? You can explore different design decisions which you otherwise wouldn't consider, and you do so by focusing on your system level design and without having to write C, C++, or HDL code, or and focusing on your algorithm development and your system level design. Okay, the implementation or the coding bit, uh, there might be some coding definitely involved in the algorithm development, but the large part of how that code translates into a end system, say an ECG monitoring device. So you might be able to code a system, code a ECG, processing algorithm, signal processing algorithm, but how it is implemented in the final device, so that it takes that burden off of you. It has multiple apps and it can scale across your different computing platforms. Yeah. So, as I said, modeling and simulation, especially dynamic modeling and simulation, is the answer to a lot of the challenges that you face in medical device development or biomedical research as such. So, uh, so model-based design is used by various highly regulated industries, and it has been used for decades. It's used heavily in the aerospace and the automotive sector, uh, wherein it is highly both of which are very very safety critical, right? The plane that you are going to fly in or the car that you're going to drive, they need to be they need to adhere to very strict safety standards. And lately, like it has also been used a lot in the industrial machinery as well as medical device. Yeah. And the FDA is actively promoting looking at modeling and simulation technologies to accelerate innovation and increase safety of medical devices as such. So um, and the same thing is called by very different names in different domains. So some people may call it in silico testing, or some people call it a virtual patient, or a uh, virtual verification platform and so on, right? So So these are links that you can visit to see how, modeling and simulation are heavily used in the medical device domain itself. Right. So, as I said, these are the stages for a model-based design process. You start with your research and your requirements, go on to a design phase, an implementation phase, and finally an integration phase. And testing and verification is done at each stage. So you design your specifications, you continuously validate and verify. You do automatic code generation, and you do some sort of certification or report generation. Right. Uh, so going over this, so it's, as I said, it's used in multiple domains, right? From automotive to propulsion control systems to aerospace to something like power generation uh, to balancing the grid and medical devices. Yeah. And all of these things have something in common, right? Wherein they have to comply to some sort of regulatory requirement. Yeah. So MATLAB and Simulink enable you to do that. So before we move on to the how do we actually go about modeling systems? So I just wanted to share this particular user story. So this is from Weinmann, based out of Germany. So these Weinmann devices basically develops medical ventilators, and their challenge was to develop embedded software for an emergency and hospital transport ventilator, like the kind that are used in ambulances. Right. So they needed to develop code for this ventilator. And what they did was use MATLAB and Simulink for modeling and simulation controllers, uh, looking at modeling, say, electromechanical valves which are present inside the ventilator, or generating production code for for the platform or for the computing platform which is present in the ventilator, maybe an embedded device of some sort, say combined with sensing devices which are there. So and finally, you need to do all of this while also looking at compliance and certification requirements, right? So, using model-based design, so their code development and their reviews accelerated by 50%, and they explored a wider design space. So, because you are not building a final model, because you are not building different prototypes, you are simply simulating. So, um, you are just by varying the parameters of the simulation, you can explore a wider design space, right? You can choose to do choose to select how a system behaves if uh, presented with a certain input, and the only thing that consumes is simulation time. It's not really costing you money uh, in terms of say developing an entire new prototype, right? And it's not even costing you time in terms of developing a new like coding more, right? Because you're simply using the existing model that you developed and simply operating it under different conditions, right? And you might have already uh, some code which is present, or some designs which are present in your uh, from say other so Weinmann had some parts or some ventilators which it had designed previously, and they could use 60% of their core design, right? So when we look at research groups in academia, or how we look at our own research as individuals or individual researchers, so very often we also try to reuse some of our code or some of our algorithms across different domains, right? So to be able to do that, we would need to uh, modularize our system in such a way, or modularize our work in such a way that it can fit into different uh, gaps which we identify. Right? So you can learn more from the link over here once I share the presentation. Yeah. So let's move on to the modeling bit. So as I said, for modeling a system, you'd need very diverse modeling approaches. Right? So most of us rely on just modeling using code. Uh, so wherein we write a bunch of code to do a particular task. Say, write a bunch of code for signal processing, write a bunch of code for designing your control algorithm, and so on. Right? But you can also, some people use block diagrams. So we as engineers understand things intuitively when we draw them as block diagrams, right? So uh, some people, so you can model your systems as block diagrams as well. Say a filter, or say your control system. So, or even your electrical circuit, right? So everything of can be more any sort of say mathematical equation can be modeled in the form of a block diagram, right? Uh, we may also kind of look at modeling circuit diagrams itself or physical systems. So wherein we are not really modeling just the equation of a circuit, but we are looking to model uh, the circuit itself with physical resistors, physical components such as resistors, transistors, valves, and so on. Right? And we might need to model different states of a system. Say if the system reacts to different things, so we may want to model the system as uh, having multiple states. So say an ECG monitor. So if you detect the ECG is normal, then you don't do anything. If you detect the ECG is abnormal, maybe notify the person wearing the monitor, or maybe notify the nearest hospital, or a nearest ambulance or emergency vehicle which is present. So there can be a. This is just me speaking off the top of my head, but most of the things that we need to do might have multiple states, right? And we often can design our systems or different states using state charts. So Simulink would be like one platform where you can do all of this multi-domain modeling. You can integrate your existing MATLAB code or your C code, C++ code into Simulink by uh, dragging in different blocks, and these blocks link back to the code that you have. You have a huge set of libraries which provide you with different functions for modeling your system. You can model your physical systems through something known as Simscape. So as you can see, so there are multiple things for electronic systems, for hydraulic systems, for mechanical systems and power systems, and so on. And finally, you can use something called Stateflow to create state charts and do any sort of event modeling over here. Yeah. So let's open Simulink first and see how all of these look. Yeah. So I'll just switch over to MATLAB right now. Yeah. So if this is the base MATLAB interface, right? If you've already used it before, you have your current folder, wherein this is the folder on your computer that it is working on. You have your command window, wherein you can enter your individual commands, say adding two numbers, doing some sort of noise cleaning, and so on and so forth, and your workspace for whatever variables you enter appear here. So leave all of that. So and focus here. So on the top of this, there is the Simulink button over here. So you can simply click on this to open up Simulink. So it might take a bit opening up when you started the first time around, but this is Simulink. So this is the window that pops up. Let me just maximize it. So there are multiple things which appear over here. So you have a bunch of examples from different domains, which you can start off with. Say something like you're doing a DSP system, say a signal processing problem. So you can create like a DSP system over here. Or say if you're doing some sort of building some sort of say logic controller, so you can look at generating controller logic for a different system. But how does all of this look? So basically in Simulink, what we do is we create models. So if I just click on creating a blank model, so this will open up a blank canvas to me. So this is my model browser. This is a blank canvas. And instead of coding things, instead of writing code here, what I'll do is I'll drag and drop different blocks over here. So say I wanted to add a couple of numbers. What I do is I'll just look at, say, the add operation over here. So this is an add block, and I'll drag it over here. Okay. I can choose to kind of also choose to kind of add in blocks right from here. So say constant value 3. I can simply copy paste this. This time around, instead of constant value 3, let me give constant value C. Okay. Now it shows me a warning. Let's see what that is. So it's an undefined function or variable. So basically, if I enter any sort of character over here, that links back to my MATLAB workspace. And I'll select a display to display things at the end. And you can simply connect up these things. So you can simply connect this block to this block. It's simply dragging and dropping. So right now, I still haven't linked this. So let me go ahead and define a number. C is equal to 6. Yeah. As soon as I define this and go back here and right click and click on, say, yeah. If I just click on refresh model or update diagram over here, so it will take a bit and it will refresh, and you'll see that the warning has disappeared over here. Right. So if I just click on run, you'll see that it added up 3 and C. The C value was 6, and it gave me the result over here. You can do the same thing by with a whole library of blocks, right from something like logical operations to math operations to you can have a bunch of sources like signal, chirp signals, noise, counters, and so on. Right. I just wanted to show you a brief highlight of what it looks like, just to give you a feel. But you can get really complex doing this, and we'll see some examples of very complex things in a bit. Okay. So as you can see in the library browser, I have blocks belonging to a variety of domains. So I have an entire block set for aerospace, something for audio, something for communications, control systems, computer vision, deep learning, data acquisition, DSP, as well as like a bunch of things for motor control, robotics, RF, and so on and so forth. And if you look at Simscape over here, yeah, so this is what I was mentioning in terms of physical models. So we'll see something of this in a bit. But so Simscape is the physical modeling library. So if you want to say define your electrical circuit and see how it functions over different conditions, so you can do that by looking at say something like say semiconductors. So you have all your electrical elements over here. uh, and you have your sources such as a DC source, a battery, or current control current source, and voltage source, and so on. Okay, so you can kind of create your electrical system over here. You can also look at mechanical systems, motors, and so on and so forth. All right, let's get back to the presentation and see the extent of this. So as I said, these are all of the steps of the model-based design process. And for the talk, we'll mainly focus on the designing of systems as such. Will look mainly at designing the entire system as executable. Yeah. So as I said, you can enable multi-domain system modeling. So you can like work with your MATLAB code. You can work with discrete time signals such as your digital control systems, your signal processing or image or video processing. You can create state machine models. So all of these would be software models which are there. You can also create continuous time models. So if you have any sort of if you're modeling any sort of dynamic system which varies with time, any sort of plant or controller models, you can create physical models of electronics, mechanics, hydraulics, and thermal systems, and also look at discrete event simulation wherein you are looking at your architecture or latency or performance modeling of your system. All of these are environment based ones. Yeah. So how in modeling and simulation, how do you kind of integrate your domain knowledge? So we as engineers, we as say electrical engineers or electronics engineers, we can either take say a first principles approach to modeling, wherein we start with what we know about the system or what we know about how the system behaves, and look at modeling that, say, as like a mathematical equation uh, for a particular, say, a DC motor or something. Or we can go towards the entirely at the other end, wherein we are looking at creating data-driven models. So we have a bunch of data for how a system responds, and we need to model how the system. We need to create a model for how the system will behave, or we need to adjust our models to compensate for how the system performs. So as I said, like these are a bunch of models which how bunch of things which lie on this entire spectrum. Yeah. So now let's look at some examples of medical device design. And how modeling and simulation will bring value to this. So basically, you look at analyzing your larger system behavior and performance through your simulation, and look at varying design trade-offs. Right? So you'll explore the design space and look at what you can minimize or maximize, and how you can iterate multiple times, and finally identify your components or specifications or sizing of the components and so on. Right? Say you are looking at a bunch of research groups from academia developed ventilators when the COVID pandemic struck. Right. So if you are limited in terms of the hardware that you have available with you, say you might have a bunch of valves lying around, but you don't know whether those valves would be enough or would work well in a particular ventilator design. So how do you kind of identify whether it works well? You do that through simulation, and say you have uh, say you were buying a particular valve from which was available, but there were say 10 different valves available, but you didn't know which one to select. So you can use simulation to identify which one would be ideal, or which ones would be ideal to kind of use in your system. Right? So all of these things you can do that. Let's look at a bunch of real world examples. I have 4 examples to show here: a pulley based surgical tooltip. So this is a tooltip which can fit at the end of an endoscope or a laparoscope. So, and it can grapple something and pull it back. So while it appears big, this would be very small, of the order of maybe like half a centimeter or barely or a centimeter. Yeah, you have uh, we have a neonatal jet ventilator for high frequency jet ventilation. We'll mainly look at this particular example over here, and look at a mechatronic, an emergency bed and stretcher. And finally, we also have another thing, endoscope reprocessing and decontamination device. We'll see if we have time enough to go into all 4. Okay. So let's look at this one first. All right. Before opening up the model, I'll just talk about what exactly was being done here. So for a neonatal monitor, they used we wanted to use high frequency jet ventilation. Yeah, so it's a type of mechanical ventilation that generates a very short jet jet stream, which greatly exceeds the rate of normal breathing and keeps the neonate uh, alive by replacing the respiratory function over here. Right? So if we want to model this in Simulink, what would we do? So we'd start with modeling a pressure source, right? So if you want to generate a jet stream, you need something uh, which generates pressure. So you need a pressure source. You need something to regulate the pressure, which is your valve. So your pressure source gets in some air input, and you need a regulatory signal, which is given by a control signal over here. So high frequency valve control. All right. So the output of this will be a jet stream, right? So you can, if you kind of model this in Simulink, you can see like the output of this on a scope block. All right. So this is essentially a jet stream, wherein you kind of you can observe how it appears in time, right? So this particular graph is generated depending upon what signal we provide over here. If it was a gradually intermittent, as I said, short jet streams which gradually increase in amplitude, so then that's how the stream will appear. The output graph will appear. All right. And finally, this is inserted into the patient's mouth or the breathing tube, trachea. So there needs to be some sort of control of the inspiratory pressure, right? So whenever we are breathing, some sort of pressure uh, is being put onto our breathing system or onto our lungs. So that is called peak inspiratory pressure, right? And so we need to, so that peak inspiratory pressure basically appears at the end of the tube that is inserted, right? And we need to monitor it to see that we aren't exceeding a particular threshold. So this is basically a control problem, right? So we need to constantly monitor the pressure which is generated by the ventilator and make sure it doesn't exceed a particular threshold, but also make sure it doesn't drop below a particular threshold so that there is no ventilation at all. So to inflate our lungs, even though we may not realize it, uh, we need some amount of pressure which is generated for air to move into the lungs, right? So, and we need to maintain a minimum amount of pressure while also not exceeding a maximum bound. Okay? So essentially what we are doing is we are monitoring the end of the jet stream and we are looking at what is the peak pressure there. So we can do that by using a peak detection block. All right. We can verify it against a particular threshold, or say a particular command which was provided. So this itself can be variable with time, or it can be a fixed sort of threshold, a fixed command. And whatever is the result, so this is a sum block, or say error block, you can say, you, and whatever the result of the error, we can give it to a PID control block, right? And what that does is comes back and the controls another valve which controls the peak pressure. So the high frequency jet is valve is controlled. So this is simply an on-off sort of setting. While how much pressure is uh, provided from the pressure source to the high frequency jet, that is controlled by maybe a valve which is like opening and closing, like so there are various degrees. So it might open, so if you so it might open to let in 50% of the air, or 20% of the air pressure which is available, right? And so now if you think of this system as a whole, right? So this is how it functions, right? So your pressure source will be your jet, your canister of oxygen, or your breathing gas which is provided, and we would know what is the pressure in the breathing, in the cylinder, or the input which is coming in, right? We know some amount of, we know the peak pressure commands, or what is the threshold which might be safe for a human being or a neonate, right? And we also know how much we want to kind of, how much is the respiratory rate that we want to set the ventilator for, right? So we know, so the normal breathing rate might be something like 16 beats per minute for a adult human being. uh, so uh, for a neonate that might be a little higher. So we may need to adjust this. So what we are doing is essentially we have all of the things which are uh, which are needed for a particular model. Uh, so we have designed that as a model, and then we are trying to simulate it and see if it functions well, and if it functions as per requirements. Right. So this is where I wanted to kind of give you an overview of SimScape. So as I said, so the pressure source over here, and so that is like, uh, it's a SimScape block. It's not. So when we are dealing with this ventilation example, so we are dealing with some amount of uh, we are dealing with some amount of physical systems, right? We are dealing with air which has to be inspired. So we are dealing with a fluid, right? We also need to ensure there is enough moisture in the fluid and so on, right? So this is where SimScape comes in, wherein you can enable, you can do physical modeling of multi-domain systems, and you can model fluids as you can see here, uh, or say something like air circulating in a ventilator, or a fluid circulating within an injection pump, right? So you can assemble a schematic and derive equations for these fluids automatically, right? You can say model things like, say, a DC motor, or say if you were doing a syringe pump for, if you're modeling a syringe pump for pushing in drugs in via automatically or at a regulated pace, then your syringe pump is essentially a motor around which you have some sort of, which is connected to a pusher, and the pusher pushes against a tube which contains the IV drug. So the motor rotates at a controlled speed, and the amount of drug which goes through the tube is regulated via that speed. Right. So, so either if you have just say the equation of capacitor or ultra capacitor here. So you can either model this as a particular equation over here, or you can model this using, and the same is modeled as your Simulink block or Simscape block. Right? So you can refine your requirements, discover your integration issues, and design your control systems, as we just saw in the previous example. Okay. So as I said, if you're working with fluids like in the ventilator example, you have an entire library for working with gases or fluids. Okay, and you have uh, a library for gas systems. You can look at pneumatic actuation. How does the gas transport work in pipe networks, and air cooling and thermal components? How do they work? Right. So if you just look at this, some of the blocks available over here, you can see that you can say a mass flow rate source, a pressure source, a control pressure source. Um, you can see a pipe. So in case you have tubing which goes from the ventilator to a patient, so if the tubing is too long, pressure will drop across that tube, right? So you have tubing with a heat source attached to it over here. uh, and it's not just this. If you wanted to create models of your own, if you want to create say blocks of your own, you can choose to do that. So similar to how this ultra capacitor block is shown. So you can choose to model your equation. So it takes in a particular input and gives out a particular output, and you can model that in this in your equations and then use it as a block in Simulink. All right. So also many of these blocks, like you can also select the level of idealization. So you can select an ideal gas or a semi-perfect gas or a real gas, and so basically it boils down to the fidelity of your model. So how accurately does the model represent a real world system? So in case you are designing an electrical circuit, so we know that properties of the electrical system change with temperature. So that way, I think this will change with how. Uh, uh, so similarly in gases, like different like ideal gas behaves very differently from a real gas, right? So before we move on, let's just open up MATLAB and maybe see that example. So yeah, apologies, I did not have this open. Yeah. So as you can see, if I wanted to model this ventilator, I have these three major blocks. So one is my dashboard, so which basically allows me to control what I'm sending in. All right. So if I just double click on this, I'll go further inside. So this is my high frequency setting. So my period, my continuous source pressure, as well as my pulse width. All right. So these are blocks which are connected to behind on to some variable, and those are taken in by these controls over here. So if we have our pulse generator that is linked to your period. So if I just look at this, so I have my pulse period and pulse width over here, your phase delay, your amplitude, and so on and so forth. I have other transfer functions which I need to define. So you can do that. Gain blocks over here, wherein I can define gain and some output. So it gives me the peak pressure in centimeters of H2O. Right? Then I have my period settings over here. So right now, if you see the period setting, it's linked to the HFV period. So it's set at 0.1. Yeah, if I change that, say So you'll see that, this value changes to 0.14. So it's somewhere here, over here. I have my constant 3. So you could have simply linked it to a variable like how I had shown earlier, in just by adding two numbers. But these blocks are provided just for you to test out things better, like, or in an easier fashion. All right. And then you have a bunch of states. So, uh, you know, so if you have a low state and a high state, you can do that. And finally, your high frequency control sequence. So as you can see, so we have combined mathematical operations with states, state modeling, and combined them with some sort of transfer function, and given that as output. And then we have encapsulated all of it into a single input dashboard. If we look at the controller, pressure controller, so it takes in the peak pressure command and it measures, like, has a gain block. It has a particular transfer function, and it's detecting peaks from the feedback, like how I had shown. Now, this is a peak detector block, which is a MATLAB function block. So if you have any MATLAB code for, say, any signal processing algorithm for finding peaks, then you can input that over here. Yeah. So as you can see, if I click on this, the MATLAB function opens up, and you're comparing your peak pressure command against your measured airway pressure, and looking at how you can do the PID control. All right. So you have your PID blocks over here. You're also doing a moving average to kind of look at the mean airway pressure and so on. And finally, we look at the peak pressure control, wherein you have your input. So this is your entire plant. Your high frequency ventilator, so your pressure source comes in from here, your peak pressure control value comes in from here, and then you have your tubes. So as I said, like, if you want to model tubes which are present in the system, you need to model that. So in ventilator, your moisture content and all of that will also be very important. So we need to kind of model tubes with heating tanks which take in moisture and so on and so forth as well. So that is where these physical blocks come in. Your high frequency control valves, multiple other tubes, and then finally your patient. So as in a tube connecting to the patient. So because each of these tubes will have different diameters, different sort of compliance, so that's why you need to model all of these systems. Right? And finally, the patient itself, wherein we are modeling the lung as a system. So some resistive components and so on and so forth. All right. I hope this gives you an idea of how complex or how simple you can make things. Right. So, and you can really go ahead and verify all of this from with your system. So if you have your pressure over here, you can simply kind of connect that back to, say, your pressure sensor at the end of the tube. So that is measured using a pressure sensor, and it is fed back to your control system, your peak pressure controller over here. Right. So it's just a sensor inside. So we've modularized a lot of it such that you can use this across different domains. So if you want another pressure sensor anywhere else in the system, you can simply copy paste this block and it will use it there. Right. So I hope this makes that thing clear. Now let's briefly look at another example before I share some resources and take some questions. Yep. So we'll look at the mechatronic emergency bed and stretcher. Yeah. So if you look at modeling and simulating a mechatronic bed, let's look at what the problem is first. So this is essentially a bed wherein you are looking at transporting patients either in the hospital setting or say an emergency occurred at say an accident site or at a home, and an ambulance came to get the patient. So you essentially have to move the patient from uh, that environment to an ambulance to the hospital, right? So during that movement, you have to keep the patient stable. So in addition to kind of tending to the patient might have some sort of injury. There might be some sort of say a fracture which might occur. If the fracture is in a uh, sensitive place like say the spine or the head, you may want to keep that stable, right? So there are a bunch of factors which have to which come into play, right? So your mechatronic bed or your stretcher essentially allows you to kind of raise or lower the patient, so from say ground level to the level at which they can be put in the ambulance. So how they can be taken out from the ambulance and so on. All right. So using something called SimScape multibody, what you can do is you can actually design the mechatronic bed. So you can actually design and this mechatronic equipment and have it animate as well. So if you are doing any sort of say modeling, so in your CAD and CAM tools, like you can import those models into Simulink or SimScape multibody and design how those models behave. So essentially, all mechanical systems will have these basic components like some lever of some sort or pulley or you know so some link of some sort which behaves in a certain fashion, right? So your hinge cannot extend beyond a particular uh, point. Say your door hinges, right? If you have a regular door hinge, those cannot extend beyond 180 degrees. So what you can do is your CAD model of a hinge can be linked to a block in Simulink or Simscape multibody, wherein you can define the degree of motion of that particular object and then have that object animate as per your constraints, right? So you can design your mechatronics bed, analyze your system behavior, and study your and monitor efficiency and vibrations which might occur. Right. So let me just show where this appears quickly. So if you just go into your library browser and if you look at SimScape, so you have your foundation library and you have your SimScape multi-body library here. So you have belts and cables, you have different sort of body elements, you have flexible bodies, cylindrical, solids, and so on and so forth, which you can combine. Your curves and surfaces, your how you can define frames of reference for that. If you have gears and couplings which are there, any sort of joints which are there, so say a 6-degree freedom of joint or a telescoping joint and or a spherical joint and so on. So you can define all of that over here. So now let's get back to this. Yeah. So if you're looking at modeling this, you're essentially looking at uh, how we can integrate this into the system. So there might be whenever you prop up the bed, there might be some issues with vibration which occur, right? So there might be vibration which occurs in the platform whenever it goes up to the final extent. So this might occur because the motor is energized when the upward motion, when there is upward motion, but it is not energized for the downward motion over here, right? So if we just look at how the position behaves, then so you know, so the position kind of varies, and then when there is upward motion, so you bring the bed from the top to down, uh, and then when you go back up to a particular height, there is some amount of damping which is required right here. So the model moves like this. So at the very top, there is some amount of vibration which occurs. So it's not as smooth. So there are some transients which appear over here, and you need to damp that because you need to keep the patient stable, right? And so this inertia is to the sudden drop in the square signal. Like, so if you are looking at switching signals for this, then there might be a negative uh, switching signal and a positive switching signal. So there might be a sudden drop in these signals because of how you model the system. But these things might not be visible to you, or these might be not. So these things might not. So we have designed the system, but these might not be ideal, right? So we can, instead of implementing it from the first design, when the first design is completed, we can simulate it and then do the implementation after verifying that issues like this have been identified. All right. So as I said, SimScape multibody can enable multi-body simulations of 3D mechanical systems. You can assemble models and import CAD models, and you don't need to derive your programs or equations. So we work very well with other software like SolidWorks and so on. So if you are if or AutoCAD, so if you are doing any sort of import from them into Simulink, you can easily get all of these joints and things imported with it as well. All right. So you can refine your requirements of the mechanical system, discover integration issues early, and design your control systems and algorithms. So this is just the animation of like how an engine is designed. So there are multiple moving systems. There are multiple things in here. So your models can be as simple or as complex as you want, and there can be as you can see, there is quite a complex model of a piston, right? And you can also generate your software for regulating this without going into hardware prototypes, right? So as I said, you can generate these 3D animations from Simulink, and you can also support C code generation. Right. So this 3D animation was generated completely using the Simulink model. All right. So let me just open up this particular model. Let me just do a quick time check. Yeah. So maybe I'll spend 2 minutes on that model before moving on. I just look at the mechatronic bed model. Uh, just a second. Yeah, I don't think so. Apologies, this model isn't opening up right away. Let's get back to the presentation and then maybe see. I just wanted to kind of highlight code generation for a bit for multiple platforms. So, uh, uh, so like if you are looking at generating code for different controllers in your system, so you can do that automatically with Simulink. So you do your algorithm with design your algorithm and model your algorithm with Simulink, finalize it, and then do your code generation automatically while combining the power of Simulink, Stateflow, as well as MATLAB to bring everything together. So how can you generate C++ code? So if you're generating C++ code, you can do that using MATLAB. You can port it to you can generate code for different numerical algorithms, or you can also create desktop applications which work independent of MATLAB. And you can also create something like web apps, which you create, which you can publish to a browser. Or you have embedded coder, which you can use to generate production optimized code for, say, something like a microcontroller unit or a DSP. You can do fixed or floating point operations. and you can do your software in loop testing or programming loop testing easily with that. So if you just look at this model of ventilator, what you can do, what we'll do is, this is the controller bit over here, right? So uh, what will happen is, so if I just look at simply the controller, uh, so yeah. So I just have if I just take the controller block over here, what I can do is I can open up the apps over here and simply go on to like a bunch of apps for C code generation. So if you open up your embedded coder or C coder, simulating coder, you can generate. So if I just type in say code generation, so you can generate code for different platforms, right from embedded code to simulate code to HDL, yeah, to your programmable logic controller, so your HDL for your FPGA and so on, and your fixed point and floating point tools. Right. So yeah, let's move ahead to the end. So these are the key takeaways from the talk. So your modeling and simulation will help you find errors early and help you test early and reduce rework. You can generate optimized code for different platforms for production use. And finally, you can also produce artifacts or reports for certification. That might not be related to the fourth point, might not be related to academic, but the first three definitely will help you accelerate your device development. Right. I just wanted to highlight a bunch of things that are a bunch of links which you can access for if you're looking at doing something on COVID-19 and the other related things. So these are some journal papers as well as some blog posts for how you can use computational approaches to repurpose existing drugs or identify new drugs for using to target COVID-19. You can actually read more from the web link pasted over here. And if you go onto the MathWorks website, there is an entire portion. So right at the top, you can see a link to a COVID-19 research, and you have blog posts for multiple things, right from using deep learning for medical imaging, deep learning to identify whether a person has masks on or off. You have ventilator examples such as the one that I showed, as well as mathematical models which are there. Yeah. To yeah, to wrap up, what can you do today? So if you're new to Simulink, I highly recommend you go on to this website, MATLAB Academy, and do the Simulink on ramp, which is like a 2-hour course on Simulink. It will introduce you to Simulink. You can if you already have MATLAB installed, I highly recommend you explore that. There are a bunch of examples in there which you can explore and learn. And if you're teaching a particular course, then you can go ahead and teach. Access a bunch of resources for teaching with MATLAB. So there are other examples wherein you can learn from industry implementations as well as implementations from academia at different research groups, and a whole bunch of videos and webinars. So whatever content that I covered today, some or the other of it might have been covered by a bunch of videos which are already present on the MathWorks website. And if you're facing any sort of issues, please post them at MATLAB Central, which is the community resource page. So I think we have it's exactly the 11:30. So in case Prasad, if you have some questions, we can quickly take them, or I'm okay taking them offline as well.
I know there are a few questions that you can quickly take up.
Sure,
I think questions are very general, so you can be very brief in answering those.
sure.
So I start with the first question. I hope you can see my screen now.
Sorry, let me just stop sharing and maybe then I can.
Yeah, yeah.
Yep. Yes.
Hold on. Yes, yes. Now can you see?
Sure. So how do you make COVID-19 diagnostic tests cheaper, and what are the ideas for developing cheaper test kits? Can it be PCR based for COVID-19 diagnostics? So one way of doing diagnostic tests cheaper, making diagnostic tests cheaper is doing some sort of batch testing. So some people are trying out combining your samples into a larger batch. So instead of testing out, say, 10 samples that you receive, you do, say, something like test only two batches of 5 samples each by combining those samples. And then if both of them turn out negative, then you can possibly skip that all those 10. So just by using two tests instead of 10, you can kind of do that easily. So that's one way of reducing costs. uh, so there are others you can read more. I have simplified it a lot more than I should have. What type of errors can we get in real-time implementations after coding and simulation? So if you're doing auto code generation, you can't. So that partially accounts for errors. So when we design coding and mathematical models, we took some assumptions like initial conditions are zero, but practically we have to. How can we overcome that? So if you're modeling any sort of system, any sort of mathematical system, what you can do is you can like specify these initial conditions. So like in the patient model that I in the high frequency ventilation, you can specify the initial condition which is there. uh, so that way you can account for that. So almost in each and every block in Simulink, if there is a sort of initial condition which is present, you can specify it. So how can we use mathematical modeling for determining uh, how much drugs were absorbed in the body after consuming a particular quantity of medicine? So if in case there are mathematical models to do that, you can like simulate that in Simulink. Also, there is a separate toolbox which we didn't cover here, which you can use to do that. So how long does it take to create a new model, and what processes are followed in its diagnostic till it reaches market? So I don't think the second part of the question I can answer as well, and I don't think it's particularly relevant to an academic setting. But there's a whole bunch of certification. If you're looking at creating new models, what I would suggest is the look at the Simulink examples. So if you're getting started with Simulink, instead of uh, creating models from scratch, what usually happens is you take pre-existing examples and then try to modify those for your approach. So, all right, thanks for the compliments, Ankit. And if it is not being used, will eventually damage our lungs. Could you please provide your input on the uses of ventilators as an engineer? So, if you just, as I said, if you just visit the MathWorks website, there will be a COVID-19 research R&D link at the top. It highlights a bunch of resources for on ventilators as well as others. So, any medical device can be modeled which can help us in identifying symptomatic versus asymptomatic patients. I'm sorry, that's more of a research question, but maybe something like a temperature monitoring algorithm using an infrared camera, or say mask detection. So, is it possible to handle multi-dimensional arrays? Yes, if you can handle arrays of any dimension that you can. Like if you have a 3D, 4D, 5D array, it doesn't matter. For detecting COVID from a breath of a person. So, uh, so I cannot. I don't. I'm not sure if that might involve some sort of microfluidics or some sort of sensing apparatus. What I can tell you, some researchers are doing are some researchers are recording your breathing sounds and using those breathing sounds to differentiate whether a person's breathing is compromised. And so it's basically lung sound analysis or a breathing sound, breath sound analysis. And we're working with a research group in IISc Bangalore, which does exactly this. But you might get more details there. And I think if you search for IISc Bangalore and breath sound for COVID-19 detection, you'll get details. They have a pretty detailed website and they're collecting data as well. So error in model, how do we have any block that can be attached to the model to monitor error at any step? Yes, yes, Ankit. So we did not really cover the testing and verification part because I thought it quite. So I made it for 90 minutes, but you can include your unit tests and you can verify whether the system is behaving as appropriate. So you can include your testing and verification to your requirements in the model itself and do that. But I did not show that. I did not cover that. In case you're interested, please write to me and I'll be happy to kind of talk to you on that as well as share some examples. Reallocate non-double matrix. So can we also use Simulink for MEMS? So there are some. So we do not really have a library for MEMS at present. However, some amount of work is ongoing in that direction. I'm not at liberty to say right now, but if you are say modeling your MEMS system uh, by yourself using a set of mathematical equations, and if you are creating a library which other people can use, please do share something like that with us, and we'll be happy to kind of work with you in that regard. But right now, the most that you can do in MEMS is, I think, model your mathematical equations there. Right. So
okay, Praful, that much is the question. Now, one very quick question from my end is
sure.
Trying to develop hardware in the loop requires some real-time simulators.
Sure.
Right. I know some OpenRT and all that software, real-time simulators are available. Do MathWorks is integrated with the OpenRT, this thing, we know that. But are MathWorks proposing something in near future for real-time simulators?
Yes. So, yeah. So actually, it's already available at present. So in case you are doing any sort of hardware in loop testing or any sort of so as I mentioned in some slides over here, there is already a solution available so that is called Simulink Real Time. Simulink RT, and then and there are multiple other things as well. And also, in case you are you're looking at buying hardware for that, so there is something called SpeedGoat, SpeedGoat. SpeedGoat, which is basically a hardware platform which can help you do that so there are educational as well as more complex hardware available from them. But you can do that, and it's available at present within MATLAB. What I'd say is for SpeedGoat, it is supported right out of the box right now. So with OpenRT and so on, I think there is some lag in terms of like the updates from MATLAB as well as the versions that they support. So that is due to their development time at their end, and that is going to happen. But SpeedGoat is usually supported right out of the box. So whenever a new MATLAB release comes in, and if you're going to do any sort of HIL testing, then you can do that as soon as a new release comes in with SpeedGoat. So because we
Okay.
developed that together.
Okay. So thank you for this. So I will get back to you because I was planning for some medical process HIL testing.
Sure.
So I will write back. I will write to you what is my plan of HIL testing and what I was trying to do. So
Sure.
maybe I can get inputs
All right.
from
All right,
you on
Professor.
that regard. Dr. Praful, thank you very much for this informative session. It was wonderful. We have received feedback from our participants on YouTube, where the session was live. So it was really, really informative, and we really want some industry people who are working on such softwares and hardware platform, because nowadays the technology needs to be end to end, just doing some coding, but not trying to get a response out of it, or not able to actuate some process that is not actually wanted. We always want that some output out of the coding should be in a position to drive something, give some output which we can realize physically. So that's a wonderful session. We will definitely share your email IDs with the participants, because there were a lot of questions about your slides and resources. So we'll share your email ID with our participants. They will get back to you. Okay. So from the organizer side, we express our heartfelt thanks for sharing your valuable time and expertise with all of us. And on behalf of NIT Silchar, we extend our gratitude as well as heartfelt thanks to you for this wonderful session. So thank you once again, Dr. Praful.
Thank you, Professor Day and Kamal. Thanks for providing the opportunity to interact on this platform. Thank you.
Thank you.
Bye-bye.
Bye-bye. So welcome Professor Nidul Sinha to the workshop, and now over to Risha to introduce Professor Nidul Sinha to our participants, as well as introducing him to the participants. So welcome Professor Nidul Sinha.
Good morning.
I would like to welcome you all to the next session of BAR 2020. We have with us our esteemed expert for this session, Professor Nidul Sinha. He is a professor in Electrical Engineering Department, NIT Silchar. A brief introduction about Professor Nidul Sinha. He obtained his BE degree in Electrical Engineering from Tripura Engineering College, now NIT Agartala, in 1984. Then he worked in Calcutta Port Trust as a trainee before joining as a lecturer in Regional Engineering College, now NIT Silchar, in 1985.
ये लोग कहाँ से ये लोग information कहाँ मिला है ये वाला?
He
इसे दिया मेरे को पूछा मैंने ही दिया.
obtained his degree in Power Apparatus and Systems from IIT Delhi in 1989, and PhD degree from Jadavpur University on application of intelligent techniques for power system optimization. His research interest is in field of power system optimization, automatic generation control under conventional and deregulated environment, application of soft computing techniques, technical forecasting, case-based reasoning, and intelligent instrumentation. With this brief introduction, I would request Professor Nidul Sinha to kindly proceed towards his talk. Thank you, sir.
Thank you, Risha Mal. Good morning. I think at first I should say that I didn't reciprocate to that Dr. Risha Mal's request for my brief CV and other things there, because I feel feverish to express I am not a great person. And specifically in the domain I'll be talking today is I'm a student in that area. So I don't know when I'll get maturity or not, because it is such an area. And of course, only one thing I'd like to share is that this is the passionate area. It is the passion. So,
Sir, you can present now, sir. Present now.
Okay, I'm sharing the slides.
We can see, sir.
Okay. So it is not brain signal. This is okay. Brain signal. This is what we have to. Without that information from the brain, we cannot do anything. So my patient is regarding to the brain because it is so much complex and difficult, and not only that, it is the essence of everything in specifically in the human society. We can do many things till we are healthy mentally. So I'd not like to great poets like Kazi Nazrul Islam, something like this. So because this is so much, if I can do or we can do something for that betterment of that brains irregularities in the brain or something like this, the mind specifically, that would have been at least something for that is my patient for that. So my talk will be at least some part of that our experience for last 6-7 years time getting associated with that in the brain signal, specifically for the silent speech or EEG based analysis. That together with that, some more extrapolations will be there in the different directions in terms of the epilepsy, or because yesterday I of course covered specifically for the brain, so silent speech reading part based on EEG analysis, EEG signals, and I'd like to go for like slightly beyond that one, and some more information related to that epilepsy, and specifically that new machine learning techniques which are not much used till today there, and it is a new directions. So and lot more things, whatever some of the things I'll be stressing on, that I'll be pointing out on the machine learning domain. So same thing, same type of philosophy or my that reasons will be applicable in the new generation, because being the new generation, again it is in the very novice state there. So a similar way the developments may be coming up for that in the new AI techniques. So I'd like to start that one with a video before the lecture for that.
Have you been here before? If this house was a crime scene and you were a suspect, you'd say no. But what if scientists could look inside your brain and work out that you've been to this house after all? Don't worry, they can't. Yet. But this is one possible future use of a technique called brain decoding. We'll be coming back to these rooms later. Neuroscientists often use brain scanning techniques like functional magnetic resonance imaging to see which areas of the brain are active during tasks. Brain decoding looks inside these active areas to identify more subtle patterns related to particular images or ideas. A typical study would put someone in a scanner and show them a series of pictures. For each picture, the scanner records activity in the areas of the brain responsible for vision. A computer program, the decoder, is then trained to associate each picture with its pattern. To test the decoder, a new picture is presented. The scanner records the activity again. The decoder then compares the new pattern to the pattern it knows from training to figure out what type of object the person was looking at.
My name is Jack Gallant. I'm a professor of psychology and neuroscience here at UC Berkeley, and my lab works on vision. That's our main focus is on the visual system. And vision is a really important thing to work on because humans are very visual animals. And when humans have damage to their visual system, they're really incapacitated. And natural vision is like watching a movie. So essentially, we were trying to build a model that describes how your brain responds. So the external world is a certain kind of movie. We want to be able to build a dictionary that will allow us to accurately predict what the brain activity would be that would be evoked by that. And then given some brain activity, we want to be able to reconstruct the movie that we saw. So on the left here, we have a movie that we see. And on the right, we have a brain. And you can see the brain activity is painted here on the side of the brain, but the brain's kind of crunched up in the skull, so it's hard to visualize. So we kind of inflate it and then we flatten it out. You can see a flat map of the visual cortex and the rest of the brain as the person watches the movie. The problem here for us is to translate between these movies that occur and this pattern of brain activity. And in the study we talked about in our paper, we just modeled this very back part of the brain, the early visual system, primary visual cortex. And that part of the brain responds to little local features in the movie, little edges and colors and pieces of motion and texture. But this part of the brain doesn't know anything about what the objects are in the movie.
Researchers have just demonstrated for the first time that it is possible to turn a person's thought into a legible phrase using what they are calling a brain-to-text interface. The continuously spoken speech can be decoded into the expressed words from the intracranial electrocorticography (ECOG) recordings. This involves using needles to record signals directly from your neuron. It is an invasive procedure, requires an incision to the skull. This brain-to-text interface was tested with many volunteers. As subjects read pre-selected text aloud, implanted electrodes recorded brain activity to an ECOG treatment. Machine learning algorithms were then used to extract the most likely word sequence from the signals, and the automatic speech-to-text methods created the text output. Error rates were as low as 25% during the study, which means the potential for the system is pretty vast.
To which this nation has always been committed and to which we are committed today.
The point to offer lock-in and investigations a valuable communication method, but it also means humans could one day communicate directly with a computer without needing any intermediate equipment. However, brain-to-text is unlikely to make it into a consumer product unless the researchers can develop a way to access brainwaves without cutting your head open and exposing the brain.
Oh, thank you. I think here I'd like to just share from the video, specifically for that that fMRI that signals were there. It is basically what it is, though it is basically is image processing domain there. And the first one started with a very simplest type of applications for that, which is very simple, just giving a pattern only. But second one is what it comes up for that the combination of different movie scenes are there, which are having multiple type of scenes and variations in that one. So and the rest part of that, they were that success rates or even accuracy rates were very poor. That are the challenging area, specifically in the fMRI. That the spatial resolution is quite high, but the temporal resolution is very poor. And of course, there are some works on the temporal resolution based on that fMRI signals. Anyway, so very important aspect of that is that last part there, electrocorticograph there, which was used for that speech, detection for that from the brain signals. The accuracy was 75%. The question is what we cannot expect every patient, every human being having the electrodes pierced into the brain, okay, to get the echocorticograph signals. So one thing could have been done or can be done is what, that we go for EEG signal there, where that electrodes are placed on the skull, on the surface of that.
I interrupt.
Okay.
Sir.
Yes. Go ahead, Rajiv. Rajiv, go ahead.
The video which you showed, the video which you showed, the participant could not see it in the YouTube. Can you please share it again? They are asking to share the video again.
Okay. Okay. Okay, then I'll just see. I Prasanjit. Oh, it is some, I think.
Have you been here before? If this house was a crime scene and you were a suspect, you'd say no. But what if scientists could look inside
Is
your
it
brain
visible?
and work out that you've been to this house after all? Don't
No,
worry,
sir.
yet. But this is one possible future use of a technique called brain decoding. We'll be coming back to these rooms later.
Not visible.
Sir,
Hmm.
hello. Sir,
Yes.
you need to change the window that you are presenting.
Is it?
The window has to be changed. You are presenting some window now. That window has to be changed to the video window.
Is it?
In the bottom, you might be seeing that something presenting tab is there. You need to sir click there,
Okay.
and
Yes.
here you can see sir 3 tabs are there.
Oh, it is asking for that. No, 3 tabs there. Window is there. It is asking
Present
for.
your entire screen, sir.
Entire screen, sir. You
Entire
click on
screen.
your entire screen.
Okay. Okay. Oh, oh, enter screen, but
And
it's
then
coming.
share.
No,
Click
that.
inside the window and share.
Sir, sir, I suppose it will be the window.
Sir, now you go to your
Let's see
video
that.
file.
Let's see that. Let's see that. Okay, I'll see that.
Yes, sir. It
It's
is
coming?
clear.
Yes, sir, can be seen.
Clear.
Okay.
Yeah.
Okay.
Yeah.
Have you been here before? If this house was a crime scene and you were a suspect, you'd say no. But what if scientists could look inside your brain and work out that you've been to this house after all? Don't worry, they can't. Yet. But this is one possible future use of a technique called brain decoding. We'll be coming back to these rooms later. Scientists often use brain scanning techniques like functional magnetic resonance imaging to see which areas of the brain are active during tasks. Brain decoding looks inside these active areas to identify more subtle patterns related to particular images or ideas. A typical study would put someone in a scanner and show them a series of pictures. For each picture, the scanner records activity in the areas of the brain responsible for vision. A computer program, the decoder, is then trained to associate each picture with its pattern. To test the decoder, a new picture is presented. The scanner records the activity again. The decoder then compares the new pattern to the pattern it knows from training to figure out what type of object the person was looking at.
My name is Jack Gallant. I'm a professor of psychology and neuroscience here at UC Berkeley, and my lab works on vision. That's our main focus is on the visual system. And vision is a really important thing to work on because humans are very visual animals. And when humans have damage to their visual system, they're really incapacitated. And natural vision is like watching a movie. So essentially, we were trying to build a model that describes how your brain responds. So if the external world is a certain kind of movie, we want to be able to build a dictionary that will allow us to accurately predict what the brain activity would be that would be evoked by that movie. And then given some brain activity, we want to be able to reconstruct the movie that we saw. So on the left here, we have a movie that we see. And on the right, we have a brain. And you can see the brain activity is painted there on the side of the brain. But the brain's kind of punched up in the skull, so it's hard to visualize. So we kind of inflate it and then flatten it out. So flatten the cortex and the rest of the brain as the person watches the movie. The problem here for us is to translate between these movies that occur and this pattern of brain activity. And in the study we talked about in our paper, we just modeled this very back part of the brain, early visual system, primary visual cortex. And that part of the brain responds to little local features in the movie, little edges and colors and pieces of motion and texture. But this part of the brain doesn't know anything about what the objects are in the movie.
Researchers have just demonstrated for the first time that it is possible to turn a person's thoughts into a legible phrase using what they are calling a brain-to-text interface. The continuously spoken speech can be decoded into the expressed words from the intracranial electrocortical cascade, ECOG recordings. This involves using needles to record signals directly from a person's neurons. It is an invasive procedure, requires an incision to the skull. This brain-to-text interface was tested with many volunteers. As subjects read pre-selected text aloud, implanted electrodes recorded brain activity to an ECOG bit. Machine learning algorithms were then used to extract the most likely word sequence from the signal, and the automatic speech-to-text method created the text output. Error rates were as low as 25% during the study, which means the potential for the system is pretty vast.
to which this nation has always been committed and to which we are committed today.
The findings could offer lock-in and mutations a valuable communication method, but it also means humans could one day communicate directly with a computer without needing any intermediate equipment. However, trying to text is unlikely to make it into a consumer product unless the researchers can develop a way to access brainwaves without cutting the head open and exposing the brain.
Sir, you can go back to your sharing window, that slide, sir. Yeah, we can see your slide.
It's okay. It's visible. Slides, sir.
Yes,
Slides
sir.
are visible.
Visible, sir. Visible.
Okay.
Yes,
So,
sir. Yes, sir.
Yes. I was talking about that. The fMRI. The first example was a simple scene of the cat and other type of that one objects were given, and then they could identify. But still, there was some limitation, like with the type of shoe. Though it could identify that it is one type of shoe, but it is not exactly the same one which was used for the training of that. So that is very simple, that sense. Okay, from the beginning of that, using the fMRI, one can come up for that, decoding the brain signals for that. When it is looked into that one, you are coming up for that, for the movie images and others, like the video scenes of the movie. It is given for that. They tried to come up with that from the fMRI signals, and it was very, very poor, very, very poor. It is not intelligible from many of that experiments. I have seen that. You may also see that from the same UC Berkeley or MIT. They have uploaded in the YouTube or something like that. But however, they are trying for that. So the problem with fMRI is what it gives a lot of spatial information. Resolution is quite high. Spatial resolution is high, but the thing, temporal resolution is not much. And not only that, one thing. Another thing is what they have gone for two-dimensional analysis for that, and which is also never true. And actually, in the brain, actually it happens that the responses happens in a three-dimensional body there. So the neurons are also placed in a three-dimensional way. So getting that three-dimensional view in terms of that, not only the spatial, in terms of even spatial as well as temporal resolution, then only one can expect a better way of visualizing or analyzing the things what is happening that one is there. Regarding the last one, because specifically I want to mention about the last one, that electrocorticograph there. So where the electrodes were pierced into the brain, and specifically the Broca's area and the Wernicke's area and the left brain part, which are responsible for the speech, identification and speech production and others like that. So there we have seen that the accuracy rate they have obtained was the 75%. 75%. So the question is what, that we cannot expect that all the human beings who are supposed to have that that type of speech problem or other type of vocal expressional problem or something like that, So that we cannot expect that electrodes to be pierced and always 24 hours like that is there. So they involve a lot of risk. So the question is why not EEG, which is a very non-invasive type, that device which can also capture signals there. But with the EEG signals, without piercing into going inside the brain, but from the top of that surface of the brain, whatever signal we capture for that, but the accuracy is very, very less. Accuracy will be not as high as echocorticograph. So now the question is what they could have done. I don't know whether they have done it or not, that one. So one thing, that means one can do the experimentation, who must have to have the provision for doing the experimentation. That for the same type of experimentation, you take out the signals for the same type of same speeches and get the signals from ECG and then EEG, and then go for that. Like what are the differences which which makes that in between the two, means from the innermost to the outer on the upper surface of that one is there. Probably if we can identify that what makes that one, also that interface problems or interface that situation there, if it can be modeled, then probably we can improvise that the EEG based model towards what coming up with that the ideal one will be that ECG, that one. So that is what there is. I don't know, they have not gone for that, they have not reported for that. So anyway, so my talk will be based on some signals. I have just I'll talk about that specifically. So I'll share some of the experiences we have been doing during our EEG based. Our is EEG based work there, and of course one I've got 4 research scholars. 3 are working on the EEG based, and 1 is working on fMRI. We'll be working for that. So EEG based on silent speech recognition, there was a project there, and then we have finished up to some extent for that one. So I'll like to share about that. What are the what are the steps there followed for that? What are the hiccups, or we can say that one is that resentment from our personal side, or specifically from my personal side. That all this I'd like to I'll be sharing for that one is there. So that like specifically for the new generation students, like researchers, they should take up that one is there, and they can go in that one, keeping in mind that my concerns are there, and so that and they go ahead with that this type of problems they can better handle the situations like this. So this is EEG only that. So EEG it has got very high temporal resolution, whereas the spatial information is resolution is very poor. That is what is there, and it is of course likely to be affected by the lot of noises as well as artifacts. So and of course that advantage for the EEG is very cheap, comparatively cheaper, and as compared to the fMRI. And another one is that it is non-invasive. Of course, fMRI also non-invasive, but this one is comparatively cheaper, so one can afford. Many people can afford that one is there, where they can go ahead with that one is there. Only the problem with that is that it doesn't have high spatial resolution. So if there is a spatial resolution is of concern, and only with the temporal resolution, it is very difficult to come out with very intelligent inferences there. So anyway, that now efforts are being made. So even in future, we are like to get associated with that combination of fMRI and EEG, and some cases TMS also. Like efforts are being made. So probably if we go for that, I have been trying for that, getting associated with the collaborative research works with some foreign universities there. That is how, just like so. Okay, I'm not going for that. Okay. This brain signal, just general talking, it is not only EEG. Even when we talk about that one, EEG, fMRI, or PC Doppler machines, all these equipments are nothing but what their objective is to capture that what is the dynamic changes in the neuronal state in the human brain. So when the human brain gets excited, that means that the neurons are to be excited. So the billions of neurons will be excited for that. So the question is what, when they are supposed to be excited, how do they, means they must be supplied to the energy. When they are supposed to be supplied to the energy, that means they will be getting energy only when what, that they get that constituents that make that energy, available for that. So one is glucose, which must be supplied to that at the same time oxygen. So that this happens, the job of this one to supply the both glucose and oxygen is what, with the help of blood only. So ultimately we see that with the excitation of neuron, it is basically, we are not seeing that, because till now I don't know that how much level. Of course, UC Berkeley, they have developed with the nano sensor coming up with that in some neuronal level, with that myelin sheath and with axon level, that whatever the changes, specifically Alzheimer's disease and others, going or targeting for that, health of every function of every neuron there, but not generally how much success is not much reported there. So normally in all other devices, their job is what, that when the neuron gets excited only when what, there is a increase the blood flow. So like TC Doppler machine also, it senses that there is an increase in the supply of oxygen, means so basically it's the blood flow, because oxygen can be supplied to the neurons only through the blood. So similar way, that EEG also means what, there will be electrical pulses there. So it is basically what, in the neuron, there is a neuron, means what, it has a, we can think that, treat that a neuronal cell or nerve cell is a electrochemical body there, because the chemicals, so there is a biochemicals there. So that chemicals, they do have that potentials associated with that chemicals. So with the concentration of the chemicals there, with the variation of the concentration, that creates a potential difference, and that is how we find out that as a potential difference is the voltage. We know this, electrical engineers, they know that any potential difference is nothing but the voltage there. So normally what we see that when there is not much unbalance in the potentials, or specifically in the ions, chemical ions there, then the potential difference will be very, very less. And when there is excitation there, or nerves are excited for that, there is a lot of unbalance in the chemical compositions there, or specifically that sodium ion and potassium ion, these two are the main constituents for that. Probably some, anyway, I'm not. So that two are there. So based on that, more unbalanced means what, you are supposed to have expected more potential difference. That is how EEG comes up for that. Similar is the case in case of the fMRI also. It is a, fMRI is almost similar to the MRI. Only difference is what it can be used with a specific function. Every function, like image, is particular image is shown there. Which part of the brain gets excited and what level? The nature of the response of the brain subject to that means what, the stimulus, a particular stimulus given for that, and that is how we want to capture. So here also what, that the responses of that means what, we see that oxygenated blood and deoxygenated blood. So based on the variations of that, means oxygen supply in the blood. So more means what, new blood coming for that means what, it is oxygenated blood, and blood which is going out for that, it is where oxygen is already utilized. So it is a deoxygenated blood. So there is a what, sudden change in the, they are also potential. Same one is what, their magnetic properties also will be changing between the oxygenated blood and deoxygenated blood, and that is how it is exploited in that one under a high magnetic field, like 1.5 Tesla, 3 Tesla, 3.55 Tesla, like the very high strong magnetic fields. There is fMRI machines there. So under that one, they create high frequency, and then sending for that, they get the response from there. And based on that, they come up for that. So basically what? So the more reactions in that fMRI, the frequency responses for that one is there. That is means what? Based on the how much is the difference between the, how much is the amount of changes in the oxygenated blood and the deoxygenated blood. Basically the blood flow only, both ways, is out in blood, flow in and flow out. So that is how means of principles are almost similar way that we come up with either this way or that way, getting that information is what is happening inside the neuronal structure there, nerve structure. Okay, so so I'm okay. This is what I see that one. This is one type of EEG recording there. We see that that electrical electrodes are placed for there. Then we find out that how the responses will be coming for that. It's quite randomized responses will be there across that one. Okay, so anyway, this is the PET-CT rhythms. Okay. Specifically, what we see that one is there in the EEG, specifically EEG signals or brain signal, because there is not EEG. EEG type used for that, but specifically brain signal, we have that different range of frequencies for that. Different range of frequencies for that is there. So, okay, this is magnetic. Oh. Okay. Okay, so we start for that means what, when the frequency is very low, very low, from sometimes what people say is the 0.1 to 3 hertz or 4 hertz maximum, that one, then we go for that. It is what delta phase is there, delta waves there, or delta state of the human brain. So normally that signifies for there when somebody is in deep sleep, deep meditative state, and then only that it is signified by the very low pulses, low amplitude pulses from the brain. And theta is for 4 hertz to 7 hertz, or sometimes 8 hertz also to say about that one is there. So specifically what there in the normal sleep or resting state. Normal sleep or resting state. And alpha is what awake state. That is what I'm just talking about, that normal talking and normal activities and all these things are carried out, which is frequencies varying from 8 hertz to the 13 hertz there. And that where the excited ones go for that one is the beta of that, or the gamma also, that one. We go for the higher and higher, we go for that means what, when the brain is excited for some excitatory stimulus or something other way like that is there. So it has to be maximum theoretically up to 100 hertz. It is assumed to be that brain signal to which can vary for that, not beyond the 100 hertz. Okay, so but ideally what one should not go beyond that 30 to 40 hertz, thing like that, to most of the cases there. So this is the different thing, similar type of MEG, and this one is the this is also similar type of the transcranial magnetic stimulation there. Because some people they have used for the similar type of fMRI, but it is specific to that particular region. For that they're sending for that specific, that like ultrasound machine type, that one. They're sending the magnetic stimulation there for the machines and getting the response from there. So this is specifically used for specifically studying that the state of the depression, depression and other that type of that states of the human brain, and that kinds of disorders also for that. It is very much used for that. Is also there. Okay, that is what it is there. What basically on the surface of this. So my question is what that means. I would say that if you go for only one type of scanning or one type of signals, one type of information, like it's only fMRI, which is having higher spatial resolution, whereas the temporal resolution is poor. And if you go for the EEG, EEGs are having less, higher temporal resolution, but the less spatial resolution there. So, and then even TC Doppler also is another type of that one is that will give us that again, that the spatial type of information is there. So if we combine these 2-3 type of signals there, and where the limitation of one signal will be overcome by the merits of the other type of signal. So the multimodal analysis will be much more effective, and it is supposed to be a more accurate one. So that is what we are planning for the in future directions for that. And here it is what we say, there's a brain, this one BCI there. And okay, one more thing is I have not gone for there. There's specifically motor imagery task there. Motor imagery task is not much. Classification of motoring action is not much very difficult as compared to speech identification or the text identification or that type of things, or even that the video images and all these things. More complex, that one. It's much more complex there. Whereas the motor this one imagery task is what it is lately. Of course, only the problem is what problem with this motor imagery task is what classification is what accuracy has to be very high, very high, because otherwise it will come out with the wrong instruction, and that will result into what wrong action, which cannot be accepted. Some wrong actions simply cannot be accepted for. So that is the one there. So anyway, so here if we look at that here, what we see that, as I was telling about that, this is the left brain. So we know that the brain has got specifically that brain there are that we have the two parts there, or we can say that and the three parts there. But brain is cerebrum. Cerebrum is there, which is so-called everybody thinks about that the human brain or human mind. That is what the cerebrum. Another cerebellum. Cerebellum is not related to that. It is more of related to that one is the motion control, coordination of the muscle and other things. All this are under the that task that functions are carried out by the cerebellum only. But that very important aspect for that our part is that the human brain means for is the cerebrum. The cerebrum, that one we have that just below the cerebrum we have that at the bottom of that we have, so is the midbrain part there, or midbrain is just above the have not gone for the just above that your spinal cord. So the medulla oblongata, and just beyond that one is there. So it is so much important for that the midbrain, and nearby the midbrain you have that hypothalamus, thalamus, and the pituitary gland. So these are so much important for that the maintaining that the state of human body. Is revolutionary. So that I don't know that what level of understanding or about that their coordinated actions and others like that is very much limited. So far as still now, whatever my experience about what these aspects there have been associated for that for some other of course activities there. Anyway, so here what if we look at, there is the left brain part is there. Out of the left brain part, this is the Broca's area. That's Broca's area and then Wernicke's area. These two are the region. That is what we have seen, that the corticographs, that the spikes where that electrodes were pierced in this zone part is there. So that means what they are specifically they are responsible for speech production or speech identification of the things there. So anyway, so okay. Now I'll just say, but I'll just share some of that one. Our method of that, how we have carried out the silent speech. Of course that project was that the way we have you have seen in that in the video there, the brain text decoding part is there. So that there actually our idea was, when my idea for the project was to identify silent speech. Silent speech, it is not words, it is not words, not even not words or not letters. So but the thing is, when actually the project was given to us, sanctioned for that one is there was a committee made by the government of India. The chairman of the committee was not from the signal processing domain, he was from the specific domain of language processing and all this thing, who doesn't know much about signal processing domain and all this thing. So he was not at all confident about that the handling of that randomized signals and how that information will be discriminative and useful for the doing classification other like that is that type of thing anyway. So anyway, there was some argument is that lastly we were forced to go ahead with the though it is silent, so go ahead with the identification of only letters, not the speech. Anyway, so again similar way we could have gone for the similar type of experiments and also we could have conducted for that one. So probably now we can go for that. We can go ahead with that one is there. This part is already there. This is how the electrodes are placed. Is a international the 1020 this one that protocol there. How the electrodes will be placed of the DEG and that one because what we are not placing the electrodes in every place. So that means there are areas which will be missed out. That is why I say that one that's spatial resolution is very poor in case of EEG signals. So we go ahead with that more and more. So what is done is we say that okay, suppose here this okay, this part, this is the based on this division of the 1020 1020 that one. Then these are the places of the locations of the electrodes there. Okay, so normally what we understand that here all the odd numbers are towards the left and even numbers are towards the right. So that when we have an electrode which is odd, even number means what is from the right brain part. If it is odd number, channel means what it is the left brain part. Anyway, so we find out that these points are there in between these areas are there. So this is located from here means what, that the regional center presumed to be means what, that neurons are that the billions of neurons there. So every region may have some millions of neurons will be there, thousands of the small region where thousands of neurons will be there. So we want to represent that the ganglion one type of ganglion, that one is there, which will represent that particular regions there. That is the concept for that. So where at the top of that the electrode will be placed, it is supposed to capture that what is happening inside that 1000. So it is basically that electrode, whatever is collecting that voltage is a what it is, a response of electrochemical response of thousands of neurons just below that one is there. So ultimately accumulated voltage is reflected in the electrode part is there. So that is how means what that resolution becomes, spatial resolution become poor. Okay, but the temporal resolution means like the earthquake type is there, seismograph type there. So that oscillations are from with respect to the time, that oscillations are more vividly or more visible in case of the EEG signals there. Anyway, so this is the same one that is there. So okay, I'll just say that what are the why it is. Of course, the question is what it. Okay, one thing is that why one we have we have based our investigation or our experimentation research on EEG only. We proposed to initially I proposed for the TCD also, TC Doppler machine also, but ultimately we have opted out for that. We have gone only with the EEG is there. So the problem with that we cannot have fMRI which runs in crores. So I do not know how many of that university, any university is having here in Indian university except AIMS and some other, because where that means not university means what the hospitals they have that they have to have, but that where academic institution where only research purposes, the way you have seen that one is there, that UC Berkeley that they were conducting experiments on that with the fMRI machines and all these things. I have doubts how many of the Indian universities are having that one, but some of the foreign universities they have that provision for that the lab facilities having that facility with fMRI, TMS, then EEG, EEG, and all like that means so the multidimensional analysis can be carried out so that we to come up with a more conclusive inferences for that, more effective and conclusive inferences. So we had no other option than to go for that EEG base, but it was really challenging for that. So what are the steps for that is there? So it has to. So what we have done is we have only developed methodologies for identifying that the 5 vowels in English, 5 vowels in Bengali. We planned for the Hindi also. Ultimately, time didn't permit because we got the machines and others almost 7-8 months late, or by the time project was delayed. Anyway, so we had to through the EEG signals. We had to go for this identifying that we have to identify from the EEG signals that the 5 vowels in English, the 5 vowels in Bengali there. And we have developed machine learning techniques right from the basic part. There is BM and then that's the even deep learning techniques are used. I'll just share some of that just very fast way, because my objective is what if you are interested, I can share the slides so that how the research was carried out. Similar way one has to go for that, because we have been following the same what the Berkeley or other place wherever they did it, that while conducting the experiment we have followed, because we have collected the data collection, we have done it from there. And of course, some people they are doing research right now. It is based on that whatever the data available, EEG data available on the ECI repository. That is okay, but the thing is there are some there are some limitations now with that type of experimentation and research. That is simply for paper publication and getting points and promotion and other. I hate, because right now I am in such a situation means what I do not hanker for any more points or any type of something like that is there. I am only worried about what before I die, whether I can do something which is tangible for the society of that. So that makes means for some sort of evolutionary research. Like you say, it has to be coming some piercing, that vertical in depth, that one something, so that like it is really effective for the society there. That is much more concern for that, because as I said about that, this is the area which is my passion. It is my passionate area. So it is not related to with my how many years I'll be having that. I have to serve the institute. No, it is not like that. It is beyond my an association with this my career or other way like that is there, because it is one part of my regular activities for that in there. So when I go for that, so what we do, we did it what we have to record that one EEG signal. So for recording of the EEG signal, what we did is that we have like made the videos and audios. Okay, so the first thing is what we will make that the subject is the students there to relax it. to relax for 2 seconds. Okay, then after that what we will present that one audio and video of that one same letter, whether A, E, I, O, U, any one letter, and it will be shown there, audio as well as video, and then it will be repeated for that. Then now it is a fixation, means what? Then after the 4 seconds, you are allowed to again fix it. Fix is fine. So we just relax, we allow him to fix it. Okay, focus it for 4 seconds there. From 5th second onward, we start recording. We start recording for that, imagining that one is there. So now the question is, for of course there may be questions about that, where during the 5th second, how many times he repeated that one? Once or twice or 3 times. That is not considered, that is not counted for that one. That could have been also done like that. Will I saw that ultimately, because that if it is repeated twice or 3 times there, ultimately the 5-second signal is a combination of 3 responses of the same thing there. That could have been another one. Anyway, the other people also, they have not done. This is in that other people, we have followed that one tradition for that. Okay, so that is how it is done there for both English as well as Bengali. That one is there. So we have gone for that. Okay, now next question is what, when we collect any data there, because this has to be, one has to do similar, even not only this one, for fMRI or any type of data also. After the data, there has to be pre-processing for that. So what is done in the pre-processing, that we go for some of the noises, inherent noises in the signal, which may creep into that one. That is, we try to remove it there. We try to remove it there. And then here what we have done is what the band pass filter means, what, because I have told about that ideally 0 to 100 hertz, or when, as I said about the 100 hertz ideal one, we can go for that because the very excited one is there. So that is what there. So we have gone up to the 80 hertz there frequency band. We have retained it. The rest parts are removed. And then notch filter is used. This is for power line frequency. For that, even if one can use the 60 hertz, 50 hertz also, just to remove that in case of any interference from is there. Artifact means they are what, they are the unwanted signals which are present in there. They are because of what, the eye movement. When there is an eye movement or there is an eye blink, if we blink, that eyelids are there, and you can see that once you connect the EEG machines to the monitor, and just see that one automatically, what you can have, everyone can see that it is very visible that that the patient subject has done something, either eye movement or eye blink or something, because that's, there will be lot of hikes and spikes available in the signals. And then again the cardiac pulses also, and there will be muscular movement. Suppose you just chew that, neck, face or something like that, some of that one, or any other muscle, if you move it there, automatically that will be reflected in the signals there. So we wanted to, so it is not that like we cannot make always like that, make the subject that, oh, don't move this, don't move this, this is, because some situations will be there where the patient may not be in a position to do that. What we can do? So we should be, techniques should be, or methods should be capable enough. Let there be these things there, but our algorithms should be capable enough to remove that, all this type of unwanted signals there. So that is what the major part of that our research one is based on that. The rest part is, there is the classification part and the feature extraction. Of course, these two parts are very important for that. All the unwanted noises are to be removed. That is compulsory for this, mandatory for that. Next one is what, very important aspect for the success of any algorithm is what, first thing is what, what are the informations or what are the features we consider for classification task. Here it is a classification task. Though I say that one is the classification is what it is, though people say that most of the majority of the classes are what, okay, majority of the classes they say that the classification is the no AI task. AI task means what, we say the classification maximum 30 to 40% task, the intelligent tasks are related to their classification. Remaining 60 to 70% tasks are related to the reasoning. Classification means what, you identify patterns. So only identifying patterns will never make you that intelligence complete. It will never be complete. Suppose I have identified this is one leg, this is one hand, this is one, that one, all these things I have identified. So this is the patterns. So unless we relate it, how this simple, the different patterns are there, how do they relate it, so that like ultimately they jointly inferred to something, some event. Some event, just like that means what yesterday I was talking about that one is a Sherlock Holmes there. Sherlock Holmes was he was narrated that the person was narrating that his story that from seeing his face, his things and others, the narration of the thing. From there means by seeing that person's face and his whole body there and a of other things that he could guess what happened. Now the question is what he was seeing that one in front of him. In front of him, he saw that the image of a person with different specific features like cut mark, these, that, and something like that. What is style of that? His body, gesture as well as body physical figure. All these things together, and he was able to combine them together in a logical sense, reasoning, so that every reason related to the some inferences, like that he was narrating a story related. So the question is what? Of course, we cannot make a machine till now that intelligent enough to behave like Sherlock Holmes. But the thing is what? That we have to try for that. So as I said about that, intelligent machines or methods, their algorithms are nothing but what? That is not classification. 30 to 40% is the classification task. We have gone for the, of course, this is there. One has to keep in mind that. Anyway, so regarding that, this artifacts were how the artifacts were removed for that. You can see that this is how that eye blink part is there. You see, eye blink is there. So much big pulse is there. Okay. Then how it is that this is upper part is what? Okay. The upper part. This one is your muscle artifact, and this one is your eye blink artifact. Muscle artifact, the frequencies are higher, amplitude is less, whereas the eye blink artifact is what very high amplitude, but the thing is what the frequency is very low, and it is corrected like that is there. So anyway, that anyway, so what we did is what we started recording that one. After that, what is the noise and artifacts were removed. So we have developed algorithms to automatically remove artifacts and noises automatically. Once it is automatically done, then we are supposed to have the clean EEG signal. Then with the clean EEG signal, now we are ready to extract that one features. Now we have to decide that which features are to be most promising one to be considered as that one, so that the classification task becomes more efficient. So for that, the classification task itself was what that was dependent on that the prominent feature selections there. So we have come up with some prominent feature selections there. And then after that, followed by what the trial selection also, because we are using the number of electrodes there and channel. Every one electrode there is one channel. So we use the 64 channels, that or 64 electrodes EEG device there. Of course, our device was having 128 channel there. It was having both the options 64 as well as 128. So use the 64 one, and which that one is there. So from the electrodes, we wanted to have that like the channel, which channel is more prominent in a given for a given particular task is there. So for that one is what weight assignment to the channels to single out those channels, or to assign that one those channels which are of higher importance with higher weights, and the lesser important lesser weight like that is there. So we developed algorithm to assign for that is there. Anyway, so this artifact removal, okay, what we have done is what I'll just say that one. Okay, so we have used here, this is the what we have done is what this is that eye blink as well as that other artifacts are there. So what we have done is the same channel is there. It is the same channel EEG signal there. So we have this algorithm has got two stages there. One stage is what is basically what this channel is, what this signal is passed through. So what is that? We have that windowing function there. The windowing function will be what shifted from one side to that, it will be sliding. It is sliding, is not exactly rolling over there. It will be jumping from the one this part, the next like that. It is jumping by that. So and then for a given window, we calculate the different features. These features are statistical features like mean, median, mode, standard deviation, and entropy. Again, then log signal, and one more also that. So we use the features there from every window, and then using that features, we use an SDM as a classifier. Means what? To identify that the particular window, it is a 0.5 second window there, windows width, and with that one, when use that features there to identify that whether that the window is corrupted or not, corrupted with the artifact or not. If it is corrupted, then once it is corrupted, then it is passed on to the autoencoder. It is passed on to the autoencoder. Autoencoder, we'll see that the later part. I'll explain. For the autoencoder is basically what that it is trained with a clean EEG signal. So when it is trained with the clean part of the EEG signal, then the moment it is what corrupted window is given to that one EEG signal, the autoencoder, so that corrupted part will be replaced with the clean EEG signal. So ultimately, what the signal means, what which the window which part is not corrupted will not be done anything. Nothing will be done. It will be undisturbed. Only corrupted part will be replaced with that clean EEG signal or trained obtained with the trained autoencoder. So like that means what ultimately it is whole signal is now cleaned up for that. Okay, so this is what this is the SBM which identifies this is the corrupted one. This is corrupted one. This is corrupted one. This one like this. So we have okay. This is what it is the results obtained by that one that with the methods there, and we find out that with the of course it is compared with the two more methods there, wavelet feature based method, and another one is ANC is there. So and the proposed one is SBM plus DA, or specifically I think this autoencoder. Denoising was subsequently it is dropped. Autoencoder was there, and we have obtained that better accuracy for that one is there. That error is also less. Error less means what? That the corrected signal is more closer to the clean signal or original signal, that one. So got it. Similarly, there we go for the SAR also, that one. And this is a correlation how that your corrected signal is how much closer to the original signal. And we find out that one is that higher the better. This SAR is higher, the better is there. So we proposed one is almost is the highest one we have obtained. Similarly, the cross correlation also, correlation part also is higher for the with this one. Anyway, so this is okay. There are two methods used for that. One is SBM as the classifier and autoencoder for the rectification part. The same way we have gone for the KNN method, K nearest neighbor method for the classifier as the classifier, and LSTM as the correction of that corrected part, that one. So similar way we have gone for that LSTM. Okay, I will go for that. I will just take care of that LSTM part when I go for that the method there, because I have to share some of the things about the LSTM part there, which is very important. But I am very much keen to share for my observations for that there. The rest part, this is what you see, that one. This is eye-blink artifact, and this is Marshall artifact there. So that is how ultimately this is what we see, that one. This is what is the clean signal. We have this one. And similarly, this also, this is the eye-blink artifact. We get the clean signal. This is muscle artifact. We get the clean signals there. This is what the graphically it is shown for that. Okay, this is for the trial selection for that. As I said about that, the different channels are there. Then we want to give that one higher, more prominent one to be more important one, higher weights, and lesser one, lesser weight. That is what. Okay. Okay. So we have used some people have used for that one CSP method for that one is there, because this is also another type of linearized optimization is other, that one is there. But we have gone for that meta heuristic based 3 algorithms were applied for that. Because you see the 64 channels are there. You just imagine that out of 64 channels, 27 to 30 channels electrodes will be prominent in that, as I said about the left brain part. So in the left brain part means for specifically Broca's area and the Wernicke's areas will be that the prominent part will be there. So we said that no, we will go for that. Let that be there, but other electrodes also nearby area also will just include for that. Anyway, that algorithm means what automatically we have considered chosen from there. So ideally, what the 64 all are supposed to be given for that, weights are there. So if it is this, simultaneous optimization of the assigning weight, so manually is simply the massive task. Next, we pause. So what is done is the meta heuristic algorithm is the best one for specifically for this type of algorithm where you have the simultaneous tuning of that optimization of the many number of parameters that one there. So we have used the 3 algorithms there, and 3 algorithms, and it is we have observed that Firefly algorithm was giving the best results there. And here we have used the trial selection and only classifiers where, because it is same LDA as well as SBM, because here the classifier is not much important in our case for this task. Our task is what? To get that, obtain the weightage importance of the different trials. or electrode signals or channels. Which channels are more prominent for that? So which are obtained, achieved with that meta-heuristic algorithm. And this is for the evaluation of the meta-heuristic performance of the meta-heuristic algorithm. There's a classifier for that. So that the accuracy is ultimately improved for that. Because this we want to improvise means more prominent means what? That those channels which are contributing more towards the better improvement in the accuracy. That is how, this is the concept of that used for that. Okay, then next one is what we have to go for. That one is that what is the feature selection for that, feature extraction and the selection for that. The first thing is we have to extract that which features to be. Now we have considered, first we started for the raw signal, cleaning the signal, removing noise artifact. Then we started with that most prominent electrodes or channels are there. Next we are ready for that. Now we have clean signals, then most prominent channels, and then now we are ready for that, means which attributes are to be or features are to be extracted for that, and so that like the efficiency becomes very high. That is what they. So for that one again, we have used the Gray-Wolf optimization method is used again. That one, as I said about that, and it is compared to GA. Here it is what it is compared to GA and Gray-Wolf means what is. I think Firefly also it is considered for that, because last chapter it was given for that Firefly, that one. So it was considered for that. It is not the modified work it is done. Because why we have considered GA, this GWO and GA, these are not so-called conventional GWO, because conventional GWO works on real numbers, but these are binary GWO, binary version of the GWO and binary genetic algorithm. So similar way that we had that binary version of that Firefly algorithm. And that is why binary that GA was almost till today also it is used for that, because of that it is considered. From that sense, it is of course very important for that. One cannot deny for that. Even there are a lot of contributions of the binary GA for that. So and is compared based on that one is there which feature are supposed to give that most prominent results for that. So here we have considered for that how we have gone for that that with the using, because we have seen that 7 features were considered, as I told about that. Okay, the based on that means what we have gone for that which features to be selected for the mode of it is something like that, means what the reduction of the features, so that like we can come up for that best combination of the features. And of course it is same with that combination, and here SBM is the classifier. It is not that at this point it is not considered as this that contribution for that. So basically what the heuristic algorithm used for that optimization of that or optimal selection of the features there. That is what is there. Of course, initial part, of course, we have gone for that here. Of course, here there was a comparison between 2 type of algorithms for that. You have you have the LDA and SBM that was there, and in the previous part also LSTM was used for the comparison for that there, and that. Okay, so lastly we have come up with after features are obtained, for the prominent features are obtained, now we are ready for the classification task. So it is now classification domain. Till now we have used the SBM and your LDA and other type of classifiers. For that means what is the standard classifier. Objective was different thing there. After that we have come up with that. Anyway, this happens to be there. I think this is research work and something like that. Anyway, so this is what here classification part we have again considered for that. These are the they are not used for the till today. That speech recognition or silent speech recognition for that. CNN is used and with the activity map, and then stacked autoencoder, that one that is also used for that. As I said about that here, I'll just discuss about that. Is that activity map is what I think that CNN works on specifically images. That the image matrix pattern. This is a matrix operation there, convolution of that matrices. So whereas that our EG signal is the frequency domain signal, there is the frequency variation, time domain signal, and you have the frequency spectrum also like that is there. So what is done? It is converted into the activity map. Is basically nothing but based on the frequency spectrum of variations of the frequency on that one. Then ultimately it is converted into the frequency spectrum, and the frequencies are represented with the colors, different color images are like that. So that is why we call that as activity map. So this image is a map. We call that one is there. So this mapping, that image function of this map is used for that this is used in the CNN. so that like the convolution and other operations are possible for that is there. So that is used for that here. And anyway, this part is okay. This part, there are, I don't know that. Okay, there are many more things. So we had gone for some of the experimentation for that is there here. This is what that map is used for, that activity map input. But then we have the convolution, and you may be knowing about that. I'm not going for with that because the deep neural network for that. So you have the convolution for that. Basically, the filters. You have the different type of convolution matrices are there. So every matrices they correspond to particular pattern there. So you have the features will be there. Then ultimately, what pulling of that, all the features together, you come up with the again pulling, and then again you go for the again second level of the convolution, second level of the again feature selection. So it's the multiple layer you come up for that. Ultimately, then you go for the prelude and then pattern. Then all these patterns fully connected, and you have that then softmax there. This is a statistical that output functions there. That is a very important, very efficient, specifically when you expect for that outputs which are having some sort of variations, probabilistic variations in the occurrence of the events. So this is the very most effective technique used for the software is there. So it is used for that with the CNN, and that one we have that this is the accuracy of that Bengali 5 vowels. Then English is, I don't know. Similarly, English also will be there. Okay, it is not included for that. So next is what the same one we have done it with that one is autoencoder there. This autoencoder there. So here stacked, there is a stacked autoencoder. This is not one layer. You have to stacking of that one after till go for that. So that autoencoder will have first initial part is for reduction of that one, that nodes. Nodes will be jumping from that. Suppose it is 64, then you just see that this is one. We got the 64. Then because we have that this feature value, so that we have the 64, this one, and then after that is reduced to the 32, then 16. Okay, and from the 16 we have gone for that softmax because we have 5 outputs are there, either Bengali or English vowels there, 5 outputs. So it is reduced from 64 to 32 and then 16. This is what the feature reduction or you can say the dimension reduction technique autoencoder very much used for that. So what is done in this case is one can go for that. One can argue for that. This is a trial and error. We have gone for that. Why 64 to 32 and that one? Like we have seen that that the half of that, something like that. But there is nothing wrong that one can go for that that other type of variations of that and go for the trial and error, then come up with that which one is most efficient. Concept is it is something like the go on reducing the ultimately you come up with that one is here is the 16 that one. So and from the 16 it is encoding part. You see that one is this is called encoding. Here is the reduce for that. Means basically these are the ways we have to find out this way. So this is encoding. So we go on reducing a number of nodes there. Then just opposite one is what from here that go for that 16, then 32, then 64. So basically this output should be ideally same as the input. So the concept is what that if we can produce that output same as the input, that means what that means that is what our efforts should be made that output should be same as the input. But how to make that can be done through the tuning of this weight. So basically what this is encoder. So first we have to find out these weights of this one, this in between that stack that one autoencoder that stack layer. So this is the weight part is there. If you can correctly identify or find the optimum values of the weights, then what will happen? This will be almost ideally the inverse of that, just opposite direction inverse of this weights there. So you use that same one there, you come up with that from there. So from there again that 16 to 32 and then decoder part that 64. Then ultimately when it's compared, if it is observed that error is 0, ideal 0, that means what these weights are the optimum weight, and we can represent the 64 features with only 16 features. Just imagine this. So this is a comparison it is done for that. Anyway, I'll talk about that. Okay, this is what it is done there, autoencoder, and both way it is there. Okay, so this is the end of that is there. So now I'll okay, here I'll talk about that. It is there. So what is done here? Here that this is here. When you go for that, how the weights are obtained. How the weights are obtained. You go for that. This is how the weights are obtained. So what happens here? This is the weight optimization. That algorithm is based same one that gradient based method there. Gradient based methods are always what they are the poor performer when there is a nonlinear, because you see you are mapping the 64 features to a domain of 16. So you are not jumping from 64 to 16 one jump, because the nonlinearity will be too high. So what you do is what 64 to then again 32, then you go for the 16, then you go for the suppose 8 or something like that, or even the 4 like that. So ultimately what you are coming from 64 to 8 or even 4 there in the multiple layers and like that. So the division of that means smaller step size, the decrement in that for feature values may reduce little bit of nonlinearity. But still, if there is more nonlinearity in between this mapping, because we are mapping 64 features from 64 features into 32, then 32 into 60. So that mapping is what, if that mapping is nonlinear, having nonlinear relationship, then the gradient based method will be miserably failed. Because as I said about that, I have that one, there is one student we have worked with that one. We have used the heuristic algorithm, meta heuristic algorithm for optimizing the weights there, and we have obtained far better results than the standard, standard gradient based autoencoder. That is what I said. Okay, now I'll just talk about that the RNN and then LSTM, as we have used also here, that one, that RNN is there. So I said we have not used that RNN there because they are proved to be, or they are said to be performing very excellent way on time series signal, time series, the random time series signal, something like that. Similar is the case the vein signal, also time series signal. So that who know that little bit of know that know about that RNN, they know that means what RNN is more specifically what they capture the local features, local informations there. So they did not consider that one, that global one there. So that is how that ultimately what, sometimes when the sequence is what, you the particular current feature value, or feature value is dependent on that, what are that feature value of that previous time at t1, at t2, t3, something like that one is there. There is a relationship for that, then that this may, in that case it will fail that to capture that information for that. So to improvise for that, because this is totally based on that short-term one, basically we can say that one is there. So we can say the local information, so locally optimize that one. So and so LSTM, so that the solution for that, this a limitation of this RNN was improvised by using their LSTM. LSTM is a long short term, means again say that one is there. Why again we are calling about that long is okay, again short term. Why it is long short term? Because short term is represents your RNN. Okay, the local part is there, and short term represents RNN part, and together with that you have the long term. So that means global information together. So every neuron will be, when it is updated for that is there, it will be using that the first information, okay, at the same time coming up with what local one also. So ultimately what that its biasing will be, or its intelligence will be much more higher as compared to that RNN one. So now my question is what, in this algorithm also, this not only this one here also, these two algorithms or whatever this here weight optimization algorithms are gradient based. They are, that also, when there is a lot of complexity, because the brain signals and others, a lot of complexities are there. So there means it is very difficult to come out with the gradient based that one. It is, you will never get the global optimal solution. Okay, ideally one may not get global optimal, but it is always what all suboptimal solution. Everybody is what the journal papers are published with suboptimal solution, because they have not gone beyond that. There is a standard one. They say that here also with this one we get reasonable results. My God, first test it on the realistic system, which are supposed to be more complex than the theoretical things we considered in our research work, thing like that. So then, and some complicated situations there, then it will miserably fail. So the question is what, so what we can do is what execution, one can use that one, saying the heuristic algorithm, meta heuristic algorithm for optimizing this RNN, as well as here. You see here it is more challenging for the, suppose you go for the gating functions, the input gate, then forget gate, then you have that output gates. These are the gating functions there. How do we represent the gating functions? Normally what they give some particular values are assigned for that. How do you trial and error these, that like this? Again, when you have the 3 or 4 parameters, so that in addition to the weights, just imagine that And this thing cannot be gradient way, you cannot do that one. This gating values are there. There's a simply manually tuned. So whereas in the if you use the meta heuristic algorithm, then there is no end, no limit for that. You can go for any number of parameters maybe included for that. You can go for that. Algorithm will find what is the best combination in terms of the gating values and in terms of the weights, what are the weight values are there. Confirm that it is supposed to, it will be giving better results than the conventional one. If it is not, I bet, I challenge for that. If it is there, I am ready to see that one. That means there is something wrong in the implementation. Anyway, so okay, this is what I say that one anyway. This is epilepsy for that. You know that epilepsy because I've been associated with the for some for our new project. We are looking for the epilepsy and ASD part specifically. I didn't cover the ASD part. The epilepsy is there. So specifically, different type of epilepsy these are available for there. So what is done? Suppose with the EEG base, it is done. So normally, what happens? You know that epilepsy. The problem with epilepsy is what? How to get the EEG signals of a person when somebody is under seizure, because the onset of seizure is random. Nobody can predict. Nobody can predict. So what is done normally nowadays wearable that wearable devices are available which can be mounted on the patients who are suffering from epilepsy regular, and based on that only they capture for that day. So what we do is here in this case you can have a look for that here also, like when we see that the different type of, specifically it is observed that here that this is of course as I said about that, you can go for that even number means even electrode number means what is a right brain, and then odd means what they are the left brain part is something like. So you can see that for some of that this one is there. This is the normal part there, normal one before the occurrence of that. That is what it is called that. So this part is what under the seizure means they say that this is what this part, this is called ictal. So this part is pre-ictal, ictal, then post-ictal. Also what post-ictal will not be exactly same as the pre-ictal part. So that the question is what we have in the few seconds to millisecond. So normally the maximum duration maybe 1 second, the most 1.5 or 2 seconds for that one seizure part will be there, and then something like that. So here, so more important part is what in the epilepsy is what how to predict the onset of epilepsy. This is very much important for that. It's initial, but everybody is working on that. So in that case, what that one can come up with that this signals there means what where there is a occurrence of changes. Some you see abrupt changes one can do, but by the abrupt changes will occur only what when there is the millisecond before the onset of seizure. So that it is of what only one thing it can be done is what you simply will develop your algorithm which will pass on the warning message signal to your relatives and others like that is there, so that like they can rush to him. But the problem with the epilepsy is what when it will occur, onset will be there. Suppose you are driving car, you are taking bath or something like something like some situations where you are walking on the road, suddenly it happens, you will collapse on the road, so people you will be run over by that, and so many other things there. So the problem with that one is what, so how to, so that when the moment the person suffers from the seizure there, automatically what should be linked with that, something like that. Maybe in today's today's situation the students may come up for that. This is not big thing there. Once it is there means we can just this is also wearable devices are available. Small that one is there, device electrode, because you are not going for that full analysis for that, just capturing that where there is a sudden changes in that word, which is what classification is very simple. So simply prepare once it occurs for that, immediately you pass on a signal through the mobile and all this, all the relatives may be informed, and together with that means where is the location of the person. Of course, warning and other things are already, it is already developed by people already there. My part is what we are trying for that is there. It is first thing is what of course I'll just go for that, is some part is there, we go for that. Okay, this is what it happens to be there, how it happens during that. This is ictal state. This is ictal state for that. So this is absence and this one is there. So ultimately what, okay, these are the they thought about that. They have thought about that. These are the stimulants there. These are the stimulants. There's different type of reasons may be there, and all these things there may be there that may excite that seizure of their onset of the seizure or something like that. So anyway, But the thing is what that where one has to look for that. One has to look for this is what one type of it is very so simple for that. You know that they use a simple neural network and use the extraction of 5 parameters there. Rise time, this one is rise time, fall time, duration of the spike, and maximum peak to peak. That one is there, these features, and then peak frequency there. Then immediately what even that may be removed also from here. You know that there is a prominent variations in that discriminative information between your normal one and onset of the ictal state there. So immediately what it is very simple. Neural network will be 100% accurate, 100% accurate. And you can go for that. This is what they have is the standard 20 EG or even 16 EG signal. Not only for that, even less than that also can be done for that. Okay. That anyway, that one has to go for the investigation for that. Means which part, which lobe is the right lobe or left lobe part of that one. Some cases it is observed that left lobe is more affected for that as compared to the right lobe is there. So anyway, so we are looking for that means what first thing is our part is what that when it is happening for that during the ictal state. First one is that pre-ictal one is that how early we can go for that based on not only one parameter. It has to be multimodal analysis for that. It is not only based on that. We can when we go for that same person with the multimodal parameters, then probably we may find out that means it is not that changes in the EEG signal maybe after some time. Before that, there may be something maybe which may be happening based on the some other parameters there. So based on that one only we can pinpoint something is going to happen, something like that. Even if the probabilistic one. So even if it is not much 10% accurate also, because you see that the being alert is not a is of disadvantage. Okay, so that is what we are planning for. That is one part is there. Another one is what during that seizure stage there, that whatever the impact of that one, that condition of the impact of this nervous that seizure and on the state of the nervous system there. That is what we are concerned for. That we'll go for. Many people are trying for that. We are also trying for not one multimodal this one. Different type of techniques will be applied for that, and not only with this one, together with that EEG, fMRI, because we will be planning for capturing the dynamical changes for that. The same person there, when it is he will be treated with a different type of therapies there. What will be the dynamical changes in his brain status there, neuronal status of his brain there, and then based on that we'll go for that means whether we are going for that. So we have to come out with an algorithm which will prove to be very useful for the doctors to identify that the treatment is going in the right direction or not. That is what we're planning for. That is there. That is so much for that. This is also very much used for that. Some people they have used for that. Because the new data, I said about that specifically. As I said about that, I want to stress on this the third generation of the neural network. This is very much in the primitive stage for that. So of course, some works are reported, but this is a spiking neural network. Actually, what happens here? I have not gone for that is there. So okay. You can see that one, the sodium channel, potassium channel. As I said about that one is the sodium ions, the potassium ions. They actually that MIT and Berkeley, they have come up with a very excellent analysis of that what is happening inside the neuron when it gets excited for that, or before excitation what happens in terms of your electrochemical behavior of that. So there they said about that is there. So normally what so based on that, this is what that in terms of the one millisecond that one, and then this is the response they have observed for that when it is excited with a some action potential. So they say there is action potential. So basically, so this is the nature of the response of a neuron. This is the nature of the response of a neuron. And now you understand that we talk about that Macolox Pete's model which is weighted and all this so man, oh my god, that was okay. We should not ignore that, because somewhere we had to start. So we started from there. Okay, that was some primitive. We can think about that, which was not never accurate one day, never accurate. You see that the question is something is better than nothing. We had nothing, so we started with something. So which was not accurate. Okay, but still some problems means what could have been solved very effectively. But the thing is, which type of problem is a lesser complex problem, obviously. So we could not achieve very excellent performance competing with the human brain or human mind, human intelligence. because of the limitation of the original tool itself was not accurate enough. So now people have come up with it. They have come up with that, UC Berkeley and MIT, they have come up with excellent way, that they have the nanotechnology based laboratories there, even piercing. Probably in future, after 10 years down the line, pico technology will be very much available for that one. Not even 10 years also, in 5 years also. Then probably we'll have more level of information about that, understanding about the behavior of the neuronal systems about that inside the brain. Anyway, so this is the information which is obtained for that one. So now that what they are using, the spiking neural network, it is considered as what? It is a dynamical model. Every neuron will be treated as a dynamical model. You have this one. Every neuron will be treated as a dynamical model. Okay, when it will be excited, then it will be excited to the maximum of the normalization. The normalization will be one, or otherwise it will come back to that. So it will be, so this mathematical model for this one is proposed. As I said, it is proposed to be a differential equation, second order differential equation. But the thing is, again, what will be the differential second order? There will be thousands of differential equations. But the thing is, what are the coefficients of that? So that makes again weird. Every person may have some difference or other way like that. It may not be exactly same, or maybe not only same person, that the responses also for the neuron may not be same as the same type, because it is too much sensitively elastic. It is called neuroplasticity. This is what neuroplasticity is explained with the help of the dynamical model. Earlier one was for non-dynamical ones. Some functions were thresholding functions. It was used for that, an activation function with the thresholding. So that was very, very primitive for that. Whereas now this one is what spiking neural network. So if we look back into the similar type of development for the multi-layer neural network, the deep learning neural network, and all this, for that one is there. Just see that when that will happen, you never know that. So this neuron is much more accurate as compared to that. Till today, whatever neurons we have considered for the activation function, that is a very, very inaccurate one. So because of that, I said that this all new is also what spiking neural network is what, or spiking neurons. You can say they're not neural network. That any new work must be with not that macOLOX what or activation function based model there, but it will be a spiking neurons based model there, and you come up with any new things that it is supposed to perform excellent way. And probably algorithms and combination of other different neural interactions and other things will be also different. It is not like normal one. It is the spikes in terms of spikes. So it is something like that also what it is pulse train type is what impulse function type, something like that is there. So it will open up so many new directions, new dimensions, and coming up with the new ways of dealing with looking at the problem there. And I hope that all new generation students and research scholars look for that. And you have to go a long way, and probably in future come up with it when it is combined with very heuristic algorithm for optimization, and it is combined with, as I said about that from the beginning, means what I said, that the intelligence is what 30 to 40% is the classification. You are doing only classification task. This neural network is classification task. My God, classification, you are just achieving that even 10% agrees, the 30% to 40% there. What is lacking in intelligence part? Artificial intelligence is what the reasoning part. So one can come up with that one, the artificial, better artificial intelligence means what? When somebody can contribute to piercing way the reasoning part. So of course, in the reasoning part also one has to look for that. Maybe that one of the reasoning is what we can say that the fuzzy system there. Fuzzy, decision making or fuzzy type of reasoning pattern, which is the inherent that reasoning part is maybe there. But it is not like that. One has to keep the mind open, because the fuzzy is what it is introduced by that Professor Jade. But okay, that is what that allows that the incorporation of a lot of logics and reasoning part will be there. So it is the beginning. There's no end for that. You go for combination of so many three things or in a different direction, and then so that like then only can in future you come up with that. You can look at that one complex problems there. And in future means what? Why I told about that from the very beginning. It is the passionate part is there. I've been fed up with that, working with some theoretical project, theoretical work. I had been in IIT also. I have seen that IIT Delhi is one of the oldest IITs there in India, and I have seen the biggest professors, very talented ACFMS professors there. But from their patentable and really contributory part from there also, it is very enable, very negligible part. Societal impact. Oh, okay, contribution is what he produced. Number of MTech student, number of PhD scholars. My God, I'm fed up with it. I don't want to produce any more MTech students or PhD scholars. That is not my count. My count is what which I can make tangible, something which society is supposed to be benefited immensely. If I can little bit of something like that is there, and this is the domain where means what, as I said about that, if the mental health of the society is such, forget about individual. Okay, few individuals, even one individual can be also rectified. I think that itself will be a very significant contribution to the society. And it is a very complex one. Means it is a very fertile domain in future. Is the domain where the lot of technology has to be given into that, put into that one is there. So that like ultimate, you see, we are doing everything and everything, not for money. Money you will get. I don't know that, you know, given that 1 crore, 100 crore, 200 crore, 100 crore, 1,000. I don't think that the person will be that happy. No, more and more money, I don't think they will be more anxious. Anyway, that is a different issue. But what is more important to me also is what, how you are how you as an individual, how you are happy, you are which I said that one is how do you feel about yourself, better as a individual, that one, and then all individuals together, then you come up with a society there. That is how it is there. So maybe okay. So maybe what my real research will start after I retire. Maybe that one, because there will be no hanky panky other, all the things will not be there, so that I can go in the specific directions for something like. So that is what I think I could touch upon the minds of, ignite some of the minds of that one is that you have to go in the direction, because nowadays I feel lot of frustrations, because every day it is coming up for that something like that. So now I feel that is what I have done. I have not done anything other than making some PhD, some MTech and all this. What is what? Of course, anyway, little bit whatever. Because another thing is very important one is what you cannot that the way of research in University of Berkeley and MIT they are doing also, we cannot do in India. In India we cannot do. I approached one neurologist there in Guwahati Apollo Hospital. I talked to him. I told him that he was eager. He is eager also now. Also he is eager to collaborate with the research work. I talked to him that is how do you treat the patient. He said that simply we ask a few questions, and then based on that, if they have any data for that EEG or fMRI or something like that is there, then we look at. Otherwise, okay, that is based on that. How do you treat? They say that it is simply. They say that it is simply with what sedative type. Some drugs which will pacify their acceleration of the human brain or human mind or something like. I don't think that is the real. Of course, something is better than nothing, because if the mind goes beyond control, there will be loss of permanent damage, maybe permanent damage to the some of the parts of the human brain. So that is, of course, that may happen also in the epilepsy also. That one we are looking for. That is anyway. That is different part there. So that is what he was telling about that. And see, that one is the contribution for that one. The majority of that, no university is having that fMRI and all this thing there. And then here also you go to the AIMS. I have seen that the wearable, that one patentable device. I have just looked for that one company is there. That is some Indian company together. They have come up with the wearable, that same one, that almost one company also they have come up with that. Seizure warning, that the easy recording wearable device there. They have come up with that. Of course, many things. I don't know what level they have got the patenting of that one is there. So okay, anyway, we are also looking for the sum of that one is there, the directions there. But this type of that pioneer or basic fundamental research in conducting the human brain and on the different direction, different experimentation, which doesn't require that the sick patients or patients, maybe healthy persons sufficient enough. A lot of research there. But once the infrastructure is created and once that the models are created for that, intelligent models are created, that can be extended for even disease mind, disease brain, or even regular brain, for the different type of regular activities. There are so many more things are there. And in future, I know there also whole world will be under brain games. Be it that the defense, be it in the your activities of other way, like there is a, be it in that, whatever way it will be there. Hope that one is what. Okay, thank you, Rajiv. Hello.
Sir, I'm coming back. We have some questions. I will be presenting my screen for questions, or you can stop sharing.
Okay.
Yes, sir. I hope you can see my screen now. I will increase the font. Yes, sir. So you can take up the questions very briefly. There may be some overlap also, sir.
Wait. You have shared, no?
Yeah, I have shared. Let me see. Maybe I have done some. Just a minute, sir.
I have not seen. It's not visible to me.
Yes.
Oh, it's coming up now. It's coming up. Okay, it has come up.
Yes.
Okay.
So
how do specialized parts of the brain integrate with one another? Yes. You see that integration, how do we that there has to be integration. I did not cover for that is there. That is not much understandable. That one is there. It has to be because different parts they have to integrate together. I know that I didn't cover for that. Left brain, right brain. Left brain is more of the mathematical, logical part is there. Right brain is more the creative images and memory and other things there. Every solution and other things has to come up combination of these two things there. Every solution you come up with a combination. So there has to be exchange of the information between the two type of different regions are there. And how do they happen? That one is there for corpus callosum. That everybody knows that. But the thing is what that the process is not much known. Probably nowadays because of the rise, as I said, nanotechnology, nanosensors are available. They are doing a lot of researches are going on the hardware, so we cannot do anything unless and until these people they come up with that. We could have done it there if we have the facilities there, but we do not have the facilities here in India. So it will be coming up. Just wait for some time. What are the biases we should avoid while brain scanning a particular image or event? Okay, please share yours. This is very important for the reason that was the first question the committee member was asking. Suppose when you asking the person to think about that something like that is or A or B or whatever it is there, but who will ensure that he is not thinking about something more, something else? You see, focusing, nobody can focus 100% to particular event there. So there will be a lot of other things there. That happens to be there. That will be the part we have to accept. So based on that only, of course, we are going for some more things there. Other research scholar is working on that. This is called baseline removal method. So that is, but that there will be hundreds of baselines will be there. That will be there. Thought process, background thought process will be there. Do these magnetic pulses have a negative impact on the neurons or any other part? No, this is not strong enough there. So there, as I said, it means what brain plasticity is there, neuroplasticity is there. They come back to the normal one. It is not there. They're plastic, so there is no problem. It will come back to that. No partial damage for the permanent damage. It does. Oh my God, this is what I said about. I'm not going for the in future uses after I retire. I'll come up for this hormone and others. The pituitary gland, mustard gland. Mustard gland. What is mustard gland? The pituitary gland. And what is midbrain? There are a lot of Indian sites, a lot of people. Not the huge work is going on in the different domain. I don't want to cover up that. There are people who think that I am an obvious or I am just worthless person. They're just talking about daydreaming or something like that. That is a different area. Midbrain and all these things that one can activate. Anyway, that is what in future we'll do that research. Okay, if I get associated with the foreign university where they have a lot of facilities there. Cure depression complete. No, it is, you see that. You see, these brain signals are not the curing for that. They are the tools to diagnose the state of the human brain. Neuronal status of that, state of the neuronal status of that. And not only that, every tool. It is tool. It is the treatment is not therapy. Cured means what? Cure means that it has to be through the therapies only. How do you do it? Through medicinal, through meditation, so many other. Meditation helps a lot. We are trying for, we'll go for that one. I don't know whether it will happen or not. Then we'll go for the so one. So in future, maybe people are doing that. What is the cause behind migraine? Oh, if that would have been known by that, there are so many causes. People think about that allopathic, concept of that. Of course, that one is there. So it is not much known till today. Does the human resonance has any effect on the enhancement or reduction of the human brain waves? Oh, that okay. I don't know that for that part. How much is the effect of the brain and all these things? That is what there. That may be that you can see this. Which is the best modality to get the most insightful image? No, it is not insightful image means okay. As I said about okay, one part is not there. Whatever things I have said about that, these are two-dimensional, either spatial or temporal. But the things have to go three-dimensional because human brain is not two-dimensional. It is a three-dimensional body. We have to get the three-dimensional picture in the different directions, and that will also it is not much done. That is another way one has to go for that. We'll go for more insightful information, three-dimensional, both spatial and temporal. That. Swanirvar. Okay, good. Swanirvar, you are good. You have so can single LED EEG be used to obtain some features multi LED? No, it is not like that. You have to understand the thing is there. Single LED EEG is what you will be targeting at a particular region. So how can you expect that? Okay, that may be what suppose that for specifically for that motor imagerators, that some part of motion of the some of the limbs and some of the parts of the body is responsible for only one particular part of the brain. That can be done. That is done. That is can be done. Oh, we suddenly changes. So there is a spelling mistake in the footer, or maybe I don't know that. Oh, anyway, that slides were app copied. It was unprofessional way. I was not dependent on making that slides professional because we have lot more works and classes and all these things. Even today morning also, I was just typing something like this. It is there. Sorry for that. Can we use the brain signal to treat the patient for evaluation? Yes, yes. So many things we are going for that. I don't know that. Yes, we'll see that one in future. We'll see that because the doctors should come forward without that that the tools and other things available, because you see we cannot do unless and until what we have the tools there. And another one is what the patient should come to us, and or otherwise what you get associated with the doctor there, and then together with the combination one can do that. What is there can be done. Effect of flicker noise over the bandwidth of here. So no, that we can not we have to remove that one is there. Okay, that is a different part of that noise predominant over the low bandwidth application there. It depends on that susceptibility of the particular organ or particular portion there, depending on that particular frequency there. Depends on that. So Nilesh Nishan question, could you please talk about the child learning behavior as much per their behavior is injected? Yeah, that is the area one has to go for that. When the ASD, that ASD part is there. That is what we are planning for that in future. ASD, autistic spectral disorder. The understanding is what from the even we are targeting for that when the baby is in the mother's womb. You understand that fetal region for that. Anyway, that are the areas where people are looking for the working for that. Either applying any single technique. Okay, that is what you have to see, that you go for more techniques there. But the thing is for that diagnosis part, once it is identified, then you have to see that which method becomes more effective for a particular type of diseases or particular type of activities there. That is how. But before that multimodal, that one has to be there, has to be carried out. Any effects of MRI mapping? No, it's not like that. Not much. Not much means okay, you have to relax. After some time, it will come back to the normal one. So it is there. The brain waves reflected to the. No, it is not that you don't. The intelligence you cannot define. You cannot figure out. Like you ask me that where is the mind? You cannot find the mind. It doesn't have that. It has it is a combination of so many things. It's not that you cannot can external brain waves affect a person's intelligence? That may be there. This was some person. There is a different part. External effect means this is what you may be distracted or another, because you see whatever parameters which affects the mind will definitely affect the intelligence. That will be there. Connect project has been large amount of interest in the recent times. Working this with the future. No, I'll say that one. If this because of Corona, otherwise this June I should have been there in that university. I was talking about that one is there. So anyway, that is excellent one. I don't know what will happen in future.
So, sir, this much is the question. This much was the question from our participants. So, sir, as usual, you are a very good teacher. We know that. But now teacher. From live YouTube, we have seen so many comments that are there. In terms of your teaching capability, so many good comments have come, and even we have received a comment that the best session of this workshop. So that was that's a good compliment.
Share with me. I'll help him so many ways. They know my email ID, no? They can share. They can, no problem. I have
we will share.
Actually, yesterday I didn't give. I forgot to give the email ID. So today I have added that email ID. So some we are asking for that. Okay.
Sure, sir. We will share. So, sir, thanks. Thanks
Rajiv,
from the organization side, sir.
Rajiv, you should be prepared for future endeavors. I was planning to have June to go there and to talk with that professor, all the neurological department experts, and it was planned for that, something like that, but it did not happen actually. Like I was planning for that seminar, and then it was decided to discuss about all the things coming for that one together with the joint and something like that in different directions.
Yes, sir.
Anyway.
Yes, sir. Definitely. Sir, on behalf of NIT Silchar, please accept our gratitude And
Okay,
thanks and for sparing your valuable time
thank
and
you
expertise.
for giving me an opportunity to share with that all new minds, new to be ignited, or if I could ignite any one of them, then I would have
Yes,
been
sir.
more than happier. That will be there.
Yes, sir.
Something like that, because they have to
Yes.
come up, because that's
Yes.
frustration every day, that kills me every day. Because that
Yeah.
I say that I'm not getting older. That is not much important. Means what, my days are getting reduced. That is what I'm closing towards my date of day. So that is what every day that haunts my mind. That is what. Anyway,
Okay, sir. Thank you very much.
Thank
And
you.
thank you, sir. Thank you once
Okay.
again.
Thank you, sir.
Thank
So, Risha, do you have any announcement you can do for the participants quickly about the session and the valedictory? Also, they have to attend. One link for the session and valedictory both. So you can give that announcement in the.
Okay, sir. So here we have concluded our 12th session. One more session is left out, that is the 13th session, and it will start from 2:30 p.m. And the link that has been given for the 13th session will be same for the valedictory function. So all the participants are requested to be present on the 13th as well as the valedictory session. So that's all from my end for this session. So we will be looking forward to join in the 13th session. Thank you.